Okay, it's about time we start. So welcome to day 5 of LXMLS. Today I have the pleasure to introduce Adèle Ribeiro, who's been joining us for now 6 years. This is the 6th time we're counting. And she's a professor in the Aachen University in Germany, and she directs the Institute for Causal and Explainable Artificial Intelligence and Life Sciences. This is a very, very important topic. Causality is probably the missing link still in AI and machine learning. So it's very important to learn about these things, and Adèle's going to teach us about it. Thank you, Adèle, for being here.
Yeah, can you hear me? Yes. Thank you. Is really, I could not say how honored I am for being always here for this 6 years that's in a row in this event. I think it's a nice opportunity to meet a lot of people and also presenting the topic of causality, which I also believe that's one of the missing link or one of the next steps to actually reach reasoning and understanding what machine learning has been providing to us. And yeah, I have to come. So artificial intelligence and machine learning, I think I cannot, I think you all know already how important it has been for, I put in bold here, what are the type of tasks where this is clearly the state of the art. So perception, right? So for detecting and classifying patterns in different images, so for example, medical imaging. For language, it's able to translate in documents, summarizing articles. For prediction, any type of predicting the future, for forecasting demand, predicting disease progression, integration of multimodality. So in medicine, there's multi-omics data sets, but you could also integrate sound, language, different types of data. It can generate samples as well. And everything, I would say, I can translate into a machine that you receive as input whatever you have in your data set. Then we have a very complicated architecture, for example, a deep neural network or a transformer. There are many of them where the idea is to first learn a representation of your data. And at the end, you take this representation and you do some sort of regression analysis. And the goal is always one quantity here, which is predicting, for example, the probability of your outcome variable, your variable y, given the set of predictors or the set of variables that you put here. And it's a very specific quantity. It's called, this is a conditional probability distribution. And from this probability distribution, you can take expectation and so on. And this is what we have been doing so far. It's basically estimating such a quantity. For example, in case of disease, predicting a disease, giving the patient features. In image classification, I can predict if it's a dog, if it's a cat, based on the image that you have as input. In language, you also can predict the next token, given what the context. In speech recognition, the same, and weather forecast is all the same. It's always a conditional probability that you are estimating, right? And yeah, and so far we are in this area where scalability is all that seems that we need. So we are in the scaling area, more data, larger models, more computation. But the question is this sufficient for scientific understanding or for understanding why everything that we are receiving from these models is happening? What do you think? Who thinks that this is enough? Yeah, so it's clearly that something is missing, and I think that's the topic of the talk, so I think you would always say that's no, right? But let's understand the subtlety of this. So I have here a very, very simple task where I want to predict the dose response of a drug, right? So that is a drug. This is a antihypertensive drug. And so the patient takes the drug, and I want to measure what's the difference between the systolic blood pressure between after, for example, 24 hours, right? So it's the difference of the systolic blood pressure. And there's just 5 variables. I simulated such a data, so I know the truth. Very simple, 5 variables. I want to predict what's the dose response, which is what's the outcome, the variable y, for this drug X? What do you propose? I think everyone's going to say machine learning, AI, let's do that. That's the first attempt. So basically you get the data and you feed in and you want to estimate this expectation of the variable y given x, and then the set S. S here is the set of other variables that I want. And what would you put here? You would put everything that you have in your data set, you would select what you would do. Everything, yeah, the more the better, right? The more the better. So let's put everything, A, B, C. I already have the X there, so everything that I have, it's in your data, is the input. Then I tried all my best machine learning models, could be random forest, gradient boosting, linear regression, could put a transformer here, but I mean, it's 5 variables. And I know the truth, that's not the point. But I got here the best of those, and I could predict the value of so this is the distribution of the predicted values and the true values. So it's reproducing the distribution pretty well. You can also see from here that the I square, which is the explainability, the percentage of the variability that's explained, and is explaining very well, 85, around 85%. It's linear, so it's definitely linear in generated data, so it's not the case here, but I'm predicting pretty well the value of y. Seems very good. I can also try now, let's do explainability, right? Explainable AI is very popular. Let's try to explain what are the variables that are most relevant for such a prediction. It seems like the variable C, which here I didn't mention in the last slide, I should mention, but the variable C is just the hospital where the data came from. So that's kind of a simulation, but the idea is that the variable X, which the drug, has been prescribed based on 2 other variables. So the doctors take some lab tests. One of them is a pharmacogenomic variant where to understand the drug metabolism capacity of the patient. The other is like a marker for kidney function, whatever. It's just some variables that the doctor usually takes to prescribe the dose to the patient, and also there are 2 hospitals. So that's the hospital type. And it seems like the hospital type is the one that's helping more for the prediction. And the X is the second one. So, okay, the drug is doing something. B is also important, A is whatever. And then I try to explain. From linear regression, we know it's just the coefficient, but for other methods, you have this several other techniques. So partial dependence plot, you have other techniques to understand what's the influence of a variable in such a model that was fit to the data. And here we see a positive trend, which says that higher drug doses are associated with elevation of the systolic blood pressure. So basically the drug is associated to an increase in a systolic blood pressure. And then I ask you, if you had this result in your hands, would you advise the doctors, the clinicians to stop using the drug? What would you say? It's very good accuracy or R square. Would you say, come on, this is just hurting? What do you think? What do you do next? Would you just stop? What are the alternatives? Would you try a better model?
Maybe other drugs.
I want to understand the effect of such a drug. So it's not the case of the drug helping or not, is other drug is better or not, is this drug good or not for the patient? Yeah. 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 So what I try next is the following. I want to try if the feature set makes a difference. And I tried all, maybe it's a bit hard to see here, but if I use all the variables, I have this I square of 85%. And it's red because it's a positive trend. And for different feature sets, So I tried all possible combinations. So if it's just X is positive, it's like 20, 21 of my slope. Just the A is 27, so changed. If I just add the B, now I have a negative trend. Now C is positive again, A and B is negative, A and C, B and C, A, B and C is all positive. So you see that the slope is changing all the time. What do you think is happening? So that's my title here, the replication crisis in science. Everyone is just getting your data set, whatever is in your hand, and publishing association results. And association results, they actually are giving you the different quantities because those are expectation of Y given different sets of variables. So those are different quantities. And my question is, should actually those quantities align or not? And what is the right one? What actually is the effect of my drug? Is helping? Is hurting? Should I stop? Should I give up? And that's the important part here. The causal effect doesn't come from a predictive modeling. It's impossible. Just from this, no one knows the answer. Just by looking at this is impossible. I could generate data where the drug is helping. I could generate the data where the drug is harming the patients, and still those would be exactly the same results. So predictive modeling doesn't give you understanding of reality. And so what's the challenge of causal inference? So I want to extract the reliable insights regarding reality, not regarding the model there. And everyone knows that the golden standard of causality is randomized experiments. How this works, right? So in practice, we just have a model. The most simple model that you can draw is like a drug, the outcome. You want to test if there is a causal effect or not, which is just this directed path or edge in my graph. But you know that there are so many other things affecting how the drug was prescribed and how the systolic blood pressure is changing in the patient. So these bidirected edge, they are representing confounding variables that exist, but it's not in your data set, or maybe it is, but you don't want to consider. And randomized experiments, they have a very interesting way of removing this confounding effect, which is basically randomizing the assignment of the treatment. So a very simple, imagine that you are in a hospital and everyone that received the drug is cured, and everyone that doesn't receive the drug is now dead, they died. Could you say that the drug is helping or not? Everyone that receives the drug is cured, and everyone that didn't receive the drug is now dead. Can you say that the drug is helping or not? Why not? They're confounding things. Imagine like a very smart doctor. They look at the face of the patient and say, you die, so I won't even bother giving you the drug. But you look very healthy, so I will give you the drug. So the person is already healthy, it's receiving the drug. The other is, the doctor don't even bother, is going to die anyway and doesn't receive the drug. So you cannot say that the drug effect, because the assignment of the drug depends on several other factors. Depends on the doctor, depends if the person can buy the drug or not. And there's so many things that you just don't know. So, but the randomization, if you had a way of actually giving the drug to very different people and also not giving the drug for very trying to capture all the possibilities of people there, then the effect, if you have a difference, for example, the group that receives the drug, this is, let's say X0 receives the drug, and the difference between the group that doesn't receive the drug, so different assignment. So there is this do, where it's just giving, is an interventional here. So I'm giving the drug here and not giving the drug, which is the second possible value of the variable x. So any difference between these two is going to be my causal effect. So basically, it's going to remove, because of randomization, it's going to remove this confounding effect. And the quantity that I get from here is exactly the, I'm predicting the value of the variable y only due to the fact that I gave the drug. And in the other group is what's the value of y for those that didn't receive the drug. And the difference is what we call average causal effect. So it's only the effect of the drug without the confounding effects. Okay? And this is clear, but randomized experiments also have important limitations, right? What are those? So many times they are just costly, impractical. It's also sometimes impossible. Imagine cancer. I cannot give cancer for a group, not cancer in another group. It's very complicated. Even randomization is sometimes very hard to achieve in practice because you have to make sure that you covered all possibilities in these two different groups. And even if you also are able to perform experiments, if you want to have a comprehensive understanding of the system, you would have to go pairwise. For every pair of variables, you would have to perform the interventions and understand how everything is connected. So it doesn't scale. So this is not possible to be done in practice. So the question is, we have a lot of observational data. So the data that's just we collect from the world. So just from the hospitals or for observations in general. Can I use this and still have the reliable information regarding the causal effect? So that's what the question of the causal artificial intelligence field is trying to answer. I think they are actually answering in a very good way. And it started a long time ago. I usually every year come here with the whole history, but today I'm just bringing Pro. Pro is, I would say, the person that visualized that you could represent the assumptions or everything that you know about the system in terms of graph theory or the graphical models. And then he developed calculus, probabilistic causal reasoning on top of this new language, right? So we have now the causal probability theory, the causal calculus, and so on. And he got the Turing Award in 2011 because of his work. This is his book. That is also a very interesting book that I always recommend if you're just starting. It's a very light reading. And it explains exactly what we saw in this example, that deep learning or any predictive modeling is has instead give us machine with truly impressive abilities. Those are the abilities that I mentioned: predictive, pattern recognition. You can connect things based on association, but they has no intelligence. You cannot expect intelligence from these models. The difference is profound and lies in the absence of a model of reality. So you need to capture the model of reality before answering your causal question. Without this, it's impossible, right? And going back to our example, I can tell you now the answer because I know what was the data generating process. So I simulated data. You can go at home and check the signs and all of it, but it's very simple equations. And the important part is that I can draw a causal diagram which represents the structure. So it's not the functions, but the structure of such a model that generated data. And in this example, I generated in a way that the drug here X and the drug X and the outcome Y, it's the association between these two variables is not only due to this directed edge, but also due to other. You see everything that connects these two variables, they create some sort of association or it helps to create association between these two variables. And the variable here, B here, which was my marker for kidney function, actually is a response for the real kidney function, which is this UBY. The UBY is the chronic kidney disease. The UCI, remember the variable C was my hospital. So that is this other variable that influences both UCY UCY could be, for example, the severity of your disease. So the more severe you are, you go to more specialized hospitals. At the same time, if you're very sick, this affects how your response to the drug. Also, there is this UXC. The UXC represents the socioeconomic status. So again, if you have in your insurance the capability of going to this very specialized hospital, you go, otherwise you have to go to the general hospital. And this also may affect the drug that you receive or the dose that you receive, depending on if your insurance covers or not. So there are several factors that could create a graph like this. A here is just this pharmacogenomic variant that's not affecting anything, it's only the variable X. Anyways, I created like this. And by knowing the graph, I may understand now what's going on. However, when you put a machine learning model, the only thing that they are trying to fit is the probability of Y given the set of predictors. And later on in this lecture, you see how to read what I'm going to tell you now, but I want to give you the intuition. In this example, all the variables, they are directly dependent of the variable Y. So you cannot, you see there's no independence between the variables and the variable Y. And because of that, this model is able to equally represent the probability of X given the other variables, although it's a completely different explanation. So I could fit a model where there's only direct causes, there's no confounding. Of course, there's no confounding because it's a machine learning model, it's not bringing any variable out of there, but it's fitting this, and this is perfectly recovering the probability of Y given the set of predictors. And this is what happened in our example. And since my goal was just to estimate such a quantity, explaining this model is only giving you the wrong insights. At least it's not the insights from this data generating model. Okay? So the causal pipeline, it goes in a different route. So how it actually works, So you start with a question. The question is always written like this. So this do operator represents the fact that you are intervening on a variable and you want to observe what's the value of the variable Y after this intervention. But as I told you, you cannot answer such a question if you have no knowledge of the underlying mechanisms. So you need to know something. And the classical pipeline, so this is how it started 20 years ago, you have to have a description, a qualitative description of the graph, which I know came from knowledge. And if you have that, then and this, as I said, it's from 1995. It started with Jing Tian. He created some algorithm to automatically given the graph gives you the following. So so as I said, you have to represent the knowledge by for every pair of variables. This is called causal modeling. And the third input here is just your data, because this is just a joint probability distribution. This you have. But then you feed everything into a machine. This machine is not a machine as in machine learning. It's actually an algorithm. So it's correct, complete, and everything follow from this. And the answer from this causal effect identification task can be either a yes or no answer. You can receive a no answer because maybe the knowledge that you incorporated here is not enough for you to identify such effect. Because you see the fact that I don't know the variable here could change. If I observe the variable, I could incorporate and then my knowledge could change for the same system. But if I have just this as a knowledge, I may have yes or no. And this is a very nice case where my answer is yes. So although it's there's like some latent confounding and an interesting structure here, I can get the right effect. And the effect is going to be an equation. So every time that I run the algorithm, I can receive a different equation. But the important part is that I get an expression that's no do. So my question is about the effect of some intervention. And I can answer that by an expression that's only in terms of probabilities that are derived from what I have. So this is my joint probability. I can get some conditional probabilities. It's just observational distribution. So I get what I have, and I map this to my answer. And from the probability, I can get the expectation. I can get whatever I want. And if you see here, that is only the variable b. For this example, I needed only the probability of y given x and b. Of course, I can do some weighting over all possibilities for b, but the expectation that's playing a role is the expectation of y given x and b only, not all the variables. And this is the answer, right? So of given data, I can estimate this, so put the hat everywhere. And this quantity is actually giving us what we need. So going back to the example, this is the answer, right? So I have here for the set Z, actually it's not only the B. Later on, you also are going to see that if I take the A and B, also solves my problem. So either B or A and B. And which means that adjusting for B or A and B is going to lead to the right causal effect. And the answer is actually that the treatment is helping and reduces the systolic blood pressure by this amount. So you can compute the right effect. And actually, this is very known in statistics. Maybe you have heard about it. So the idea of not adjusting, so the failing to adjust for some confounder. So this path here, B is a confounder because it's creating association between X and Y. And this path, I hope you also are going to understand later on, this is an open path creating a confounding. This is a confounding path. And if I don't adjust for B, this path keeps creating association. And then when I compute the correlation between X and Y, I compute the composed association for these two paths. So if I don't adjust for B, which means this yellow line here, this is together, the directed edge plus the confounding effect. That's why it's positive. But once I condition on B, I remove the influence of B, and then it goes only to the influence of the directed edge. And this is called Simpson paradox. So I can reverse an association by conditioning on a variable or not. Also, there is the Bergson's paradox, which is a conditioning on collider. So this C is a collider because there is an arrowhead on both sides. So I call this variable as a collider in this path. And if I don't condition on C, this path is not hurting anything. But the point, so if I include this to my model, I create a spurious association. So I create an extra source of association between X and Y. And this can also reverse the sign. So if here is an expectation of Y given X and B, which is already conditioning on B. But once I put the C on my feature set, I go back to the positive trend because I incorporate this path here. So you can now understand why you can flip this sign and have completely different results is because you're asking different questions. So your question, that's the causal effect, won't change. But there is a very particular way of estimating without biases. All right. And so I said this is the causal pipeline. And I'm going to inspire you because sometimes people say, okay, I never have the knowledge of the graph. So can I actually improve this? And yes, you can. So I hope also by the end of this lecture, you see that you can replace completely the causal diagram to something that you can learn in a fully data-driven way through causal discovery algorithms. And this is also a nice example because only from observational data, I could recover almost everything that I need for this graph. So this circles means that I don't know what was happening between A and X. Could be a directed edge, could be a bidirected edge, could be both. But for sure, B has a causal effect to Y, X has a causal effect to Y, and C is just creating this collider path here. So from this pack, you also can use now some tools. As I said, this can be learned through causal discovery. In this case, it was used the fast causal inference algorithm that I'm going to also introduce in this lecture. And from that, we extended the entire pipeline, and you can have again, the same answer and the same formula in a fully data-driven way. So this was a paper. I have the ID algorithm for PEGs, and the entire pipeline can be done in a fully data-driven way, right? So there's no excuse to not do causal discovery. You don't need any knowledge. You can learn the graph, you can learn the right expression and get the right effect, even accounting for latent confounding. All right, so that's the outline. I hope I motivated you in this lecture. The outline is I will go over some foundations in causal inference, which is going to introduce what is a structure causal model, a causal Bayesian network, the Pearl's ladder of causation, which I will try to connect with the talk we had with from Eric Ching, where he talked about the ladder of intelligence, and this is pretty much the same ideas. Then I go to the foundations for causal discovery. So you need to know what actually Bayesian networks is about, condition dependence and separation, and Markov equivalence classes. So just for me to know who have heard about all these topics before. Yeah, so this I expect that is going to be kind of knowledge from all of you, but I will go very slowly for those that have never heard about it. But then after the break, I would go more deep into the causal discovery, and I will explain how constraint-based methods which use condition dependence tests, they work, and especially the fast causal inference, because in my opinion, all the advances we have today are based on this. So it's the most important algorithm. But I also go to the recent advances that we had in the future, here in the present. And then I go close to causal effect identification, which goes to the causal adjustment. This is something that I think it's necessary for you to know, because it's very used out there in the potential outcome framework for inverse probability weighting and so you need to know what's going on. But of course I go and explain the ID algorithm, not in deep, but I will explain that this exists and then you can use in your pipeline. All right, questions up to this point, or any discussions you want to bring? All right, so the structure causal model is something that we are always looking for. So if we have it, we would have the true model behind the data. If you have the structure causal model, we have everything, and there's no task. You can do everything. It's the full explainability for all sort of inferences that you can think about it. But what is this? So this is just a set of things. It's a tuple. So the first one is this set of variables V, where is the variables you have in your data sets. We call it endogenous variables, but could say observed variables, just the variables you have in your data set. Of course, there are other variables that are important. Those are the U's that I used in my example. They are there. You cannot forget about them. And they are called exogenous variables. And we usually are interested in representing or like learning the observed, how the observed variables, how you explain the observed variables in terms of the other observed variables. So the parents are going to be other endogenous variables. We call them parents because later on you see that's a graph. And the other variables which are also cause, right? It's also an argument of the function for this variable vi, but it's exogenous, so we put just a different letter. It's just a function of other variables. And to have the full description, we also would need the probability of these exogenous variables. So this completes the specification. So if I have all of this, I have full explainability, but it's too much. I'm requiring, not saying that there is only a function, but also which function it is. I'm not saying that it exists as exogenous variable, but also the probability distribution is too much. There is even some assumption that we usually make, but some people are relaxing this, but most of the field are still assuming that you have a way to estimate the order. So one process leads to another, which leads to another, and this doesn't form a cycle. So this is a recursive modeling. So being recursive means no cycle. And as I said, if you had it, let's just go, so keep it with me, but if you had it, you could do everything. You could causal effect, counterfactual reasoning, you could do everything. So causal effects are just effects of intervention. And from the model, so if this was my model, so just two variables, X and Y, and I could have, this is the simplest example that I also mentioned in the randomized experiments slide. So two variables, they can be functions from one of each other. So here Y is a function of X, but they can also have other variables as cause. And sometimes you have a shared cause. And these shared causes, they are called confounders. Those are the most dangerous variables for causal reasoning. But it's okay if you just get data directly in a passive way. You get something that we call observational data, which leads to the observational distribution. And from that, you can compute the probability, the joint probability of the whole set of observed variables. And you can do what we are used to do from here. You can derive these conditional probabilities. And every time that a variable, for example, the probability of Y, given the set of variables X or a variable X alone, is different than just the probability of Y, this is definition of conditional dependence. So this means that X is dependent of Y. Then usually observing X helps to predict the value of Y, right? So just by having dependence helps prediction. I'm not saying how this helps. But if you want to do an intervention and only observe what happens with the variable Y after changing the assignment of the variable X, then the assignment is no longer depending on functions or variables, is like a fixed value. And from such a model, which we call manipulated model after intervening on X, if you had a way to induce the probability distribution for such a model, this would be the interventional distribution. And the distribution has this notation. Then if you have a difference between the probability in this system and the probability in this system, then means that X actually matters as a causal effect. Because the only way that the X is helping Y is now through the direct argument, no longer through these common confounders, these common causes. So these common causes no longer appear here because I fixed the equation. And once I fix the equation, the only way that X contributes to Y is through via argument. And then you mean, if I had a way to do that, I have a way to compute the effect directly. All right. So the structure causal model encoder is an encoder of functional knowledge, function and distributional knowledge. But this is unavailable in practice. No one, I mean, some people try to do that. Structure equation modeling in statistics. So some people are looking after this structure causal model and hoping that's the true one. So it's pretty hard, but it's usually unavailable. I would not try to achieve this. And randomized experiments, as I said, many times is costly, unfeasible, and unethical. So what is left to us? Can I then identify the effect of interventions from observational data without specifying the SEM, without running an experiment, and hopefully without specifying the distribution, the functions, and everything in a completely non-parametric way? What do you think? Is this possible? Seems like a dream, right? But the answer is very positive, is yes. And that's how the field is started. So first, the answer is yes, but you need some sort of structure knowledge. And we encode this as a graphical model, right? It's a graph. And I will explain what's the causal diagram now. So the causal diagram sometimes is called causal Bayesian network. So maybe you have heard about what a Bayesian network is, right? Who have heard about what a Bayesian network is? Yes, I hope. But that is a causal thing, and this makes the whole difference. So the causal Bayesian network, it is a Bayesian network because it encodes all conditional dependencies and independencies among the observed variables. But there's something more. It encodes the right direction of the causal mechanisms. So we really need the directions to follow the causal mechanisms. It cannot be any direction. So let's see. So as I said, the structure causal model many times is unavailable. But in some situations, you know, the structure is less than the functional description. This description is the following. So I'm not writing what are the functions, so the F's are just F's here. The probability, I'm not saying which distribution is here, but this is enough for drawing the graph. The graph, this is the graph from the example. So I say that X is a function of A, B, and some UX. So first I started drawing edges from the arguments to the variable itself. So you see that A and B is pointing to X, and the Y variable is a function of just X from the observed variables. Of course, that is the U. They are the U variables. So if you would follow the same idea, you would put the U's pointing everywhere. I removed the C here just for sake of space, but there is one confounder still, that's the UBY, and this UBY means it's a common cause of both. And it's in gray because it's in the set of U, it's just not present in my data set. However, there is a way to encode. This is the right way of encoding, so it's all correct, but it's too bushy, it's too dense. I don't like to see all these nodes. So what people do, they hide all these U's that are just pointing to one variable, because I said that the dangerous case is the common latent cause, which creates this confounding, but the others are not dangerous. So I just hide them. And I put a bidirected edge for the dangerous case, and the others, I just hide them. So this is the simplest representation for my causal diagram, for my system here, but the U's are there, right? You need to remember that the U's are there. And I usually require, so in the classical pipeline, I used to require this. So if you had such a knowledge, you would follow the pipeline. But as I said, what about the causal model identifiability? We were like always aiming to get there. Why is this a problem? So what happens is that from the equations, from the set of equations, getting just the graph, that is a loss of information, right? Because one graph could encode many different ways of this confounding. Could be one variable, could be many variables, could be several. This function could be different functions. So once you move from the structure causal model to this representation, which is either the graph or the probability distribution or data, you lose information. Even if you perform an experiment, if you don't have the equations and you only have the representation in a graph or the probability distribution, you lose information. Going back to here means recovering information. And of course, we require some assumptions if you want to go back. And in practice, this is what we usually want to do. We just have data which has not all the information I need, right? So for example, just two variables, X and Y. And that's why correlation doesn't imply causation, because we are always used to look at two variables and we don't want to make any assumptions regarding these two mechanisms. And the idea of trying to recover a model for this X and Y doesn't get the full picture. It's just getting this probability distribution. And let's go back here. So for example, one model here where it's described by X pointing to Y, this could lead to the same data set. I could also get, and this could be like your fitted model, but there are many other equations that you could change, just the parameters, the distribution, which would also have X as an argument of the function of Y, and it still leads to exactly the same data set, the same numbers, the same everything. And the problem as well is that you can now flip the graph. So you could have now Y pointing to X is a function now that Y is the argument and X is the outcome. And there are many parameterizations, or like just a confounding, there's no causal relationship between them, or both. And all of this, you could generate different models with different parameterizations that would lead to exactly your same data set. And when you fit a model to answer such a question, there's no guarantee that you actually got the true model, right? So the true model, for example, could be this one. And then when you start explaining your fitted model, it's just explaining the wrong things. It's completely different. And there's no point of doing that. right? So there's a lot of explainability tools, which helps to understand the model that was fed to the data. But this doesn't give you insights into the reality. So there's no understanding from that. Okay. And an important thing here is that you have to look that even if you had all variables in the world, which we call sometimes causal sufficiency or causally sufficient models, even in this scenario, you still have ways of having two different directions, and in each of these directions, we would still have different models. So even if you have the right graph, you still have multiple models. Right? So achieving the right SCM here, I think is too much, right? But this is what Pearl in the Book of Why classified the 3 types of inferences that you can do. And he called this as the Pearl's ladder of causation. I mean, he called just ladder of causation. Now everyone calls this Pearl's ladder of causation. And there is a nice figure here. This comes from the Book of Why, where we have 3 types of inference or tasks. The first one is like I'm just observing, right? The observing means I have the observational distribution, so I have associations. And from that, I can actually solve a lot of tasks. Those tasks is what we have been doing for like many, many years. They include machine learning for supervised and unsupervised learning, decision trees, deep neural networks. LLMs is a kind of stretch here because you also have reinforcement learning there. But if you just use observational data to train that, you are still in this layer. And the answers that you can answer are like, what does observing X tells me about Y? So I can predict pretty well Y, but I cannot explain why this happened. It was our example. But I can still answer like, what does a symptom tells me about the disease? It's all good. I observe things and I can predict stuff. So this is like classification tasks, and it helps. But once you start asking why, what was the effect of the drug alone? Then it's a different question. That is this do. What's the value of Y after changing only the value of my drug, or only on the variable X? And I can condition on any other variables. Now you require experiments. So you can run randomized experiments. In machine learning, we have reinforcement learning. So as long as you are performing experiments in a way that you collect the real causal effect, or like in the lecture here, we will see how can you do causal effect estimation. You can answer now on average, because its probability is not the value of Y, it's the probability of Y. So on average, what happens to Y if I intervene on X? Okay, so it's probability. So will my headache be cured by an aspirin? I can still guess because it's probability, but now it's in the right direction. I can tell it's a negative effect, it's a positive effect, it's an average. But then you can also start asking more complicated things, which is more individual things, more value-based information, which is counterfactual. Now I need the full model. I mean, maybe it's too much, but usually require the full model. And some people are trying to go that. Let's fit a deep neural network to recover the structure causal model under certain assumptions, maybe too strong, you get it, but you would have the knowledge for answer such a questions like, what would have happened to a person, to an individual that already received, for example, I received the drug and I was cured. Was actually the drug that cured me, or I would be cured anyway, right? Was the aspirin that stopped my headache? It's like very individual. So you need to know not only the distribution, you need to know the value. And for that, you need to have the distribution of the error terms, you need to know the functions, you need to know a lot. And that's the challenge, because usually we want to do cross-layer inference. We are here only observing in a passive way, sometimes collecting some here or there, some experiments, but you want to go up in the ladder. You want to infer causal effects, you want to do counterfactual reasoning, and that's the challenge. And there is even a theorem that was proven, I think this was known from several years, but it was proved proven by Elias Barenboim. So he proved that the causal ladder, or this causal hierarchy here, that's called causal hierarchy theorem, never collapses, or almost never collapses, which means that for almost any structure causal model, the layers are going to remain distinct. This is like, from data alone, I cannot get one graph. I will have just partial understanding of such a graph, which you saw in the output of the causal discovery. There's the circles, because it's a class. There are many graphs that could fit to that data. The same thing, like from one graph alone, you cannot get the SCM. There are many SCMs there. And so they are going to always remain distinct. But maybe you can learn a little bit from data. Maybe you can get there, but you need to know which parts and why. And I'd like to connect with the lecture from Eric Xing, because I really liked this ladder of intelligence. It seemed very connected to this ladder of causation. And the scene was the book intelligence. So it's true. The machine is just reading books. It's not, so it's going to have like observations alone. So you can do prediction, pattern recognition. You can get maybe imputation. Some people are asking me, can you now do imputation with this distribution? You have to remember, only if you are in this case where it's completely at random, like the missingness of the data is at random or completely at random. There's no like hidden mechanisms explaining why the data is missing, which is strong, I would say, but you can kind of do that because you just need to estimate the probability distribution, the observational distribution. There are many tasks that you can just do by just observing. But once you start asking about physical intelligence, it's like outcomes of actions. What happens? Like you need a model, but such a model doesn't need to be as complicated as the SCM. You can just know if you are okay to have the probability of such an action. So what's the probability of the outcome after performing such an action? You just need the second layer here, is the interventional layer. So you can estimate, for example, you can simulate now. But remember, it's probability. It's not going to give you the right value. It's going to give the expected value of it. So you can do some sort of populational level rule out or simulation. And for that, you just need the causal graph, or not even, right? I showed you that from data alone, you can estimate the graph from causal discovery. It's not the full graph, but at the end, you need an identifiable causal effect. So for one quantity alone, maybe that's just the effect of X on Y. You don't need the whole graph, and you don't need knowledge at all. You can estimate, but you have to do the right effect identification task. And for counterfactual reasoning, which is more individual, for example, what is a digital twin? These people are talking a lot about it. Or like, what is a counterfactual? So what happened to a person if something was different to her? Like, what's the cause, the root cause analysis? All those tasks, they require to know more individual level inference. And of course, if you have the SCM, you'd answer, but you don't need it. So if you have just one query, so if your query is just about what happened to that particular person that took the drug X, what happened if the person didn't take the drug? And the why is like, I know what's happening in a reality, and now it's like counterfactual reasoning. So I know that the person took a drug and it was cured. What would happen if the person doesn't take the drug? Would be cured. So I know the outcome in one reality, and know what was the action in such a reality, but I want to know the output in a counterfactual reality. And for that, there are tools for that. You do like full abduction, action, prediction. And there is counterfactual identifiability that sometimes you can do from the causal diagram. You don't need an SCM. And sometimes you can impose some assumptions, for example, monotonicity. But if you are interested in knowing how the structure causal model can be identifiable fully, you can read this paper, and they tell you that's basically impossible. The only case is like if you have all variables, which causal sufficiency, then you know that the functions are all monotonic, and monotonic in one dimension. If you go to higher dimensional, now you have a notion of rank order monotonicity. And you need to know what are the distribution of the variables. So if you assume Gaussian, it is good. So there are a few cases where this works. So for example, the additive nonlinear models under causal sufficiency, they are identifiable. So if you are sure that your scenario is in this case, maybe you can go after the identifiability of the SCM. But maybe you don't need it. Maybe you just stick with your carry, and there are very specific tools for answering that, sometimes even just from data. Okay, and this is what the field tries to characterize today. All right, so now going to Bayesian. Oh, questions up to that point?
How does one know if their system is causally sufficient?
Impossible. I don't work on this scenario. That's why I said I represent the fast causal inference algorithm because it accounts for latent confounding. But sometimes you are in a very restrict scenario, like, I don't know, maybe, no, I don't know. I won't start guessing here, but for me, this is extremely strong. But maybe you are in a very simulation scenario where you know all these pieces. Some people can actually even simulate their brain, and they think that this is everything that you need. But if you don't believe on that, you don't go through that, I would say. All right, so Bayesian network, as I mentioned, is still trying, it's a graph like the causal diagram, but it's only representing the joint distribution probability, or the set of dependencies and independencies. And I said there are many of them that implies the same set of conditional dependencies and independence. So Bayesian networks doesn't recover causality, but it's a good component. So let's see how it works. So it's a direct acyclic graph, or sometimes we call a DAG. And it follows some kinship notation. So that's why the cause is here. They are the parents. This is, I think, so X and Y are parents of Z. Z is a child of Y. Anyways, it's very intuitive. A W is a descendant of X, also a descendant of Z. Y is, it's very intuitive. So that's kind of it. But when you have latent confounding, which is bidirected edges here, you call the graph with a different name. It's still a DAG with bidirected edge. So some people say DAG with bidirected edge. Others change the name to acyclic directed mixed graph. Just mixed because now you have a mixed type of, anyways, it's just names. But it still have the same terminology. So X and Y are parents. And there is a difference here where there is a spouse. A is a spouse of W. Just names. If you are in the causal sufficient scenario, we are also called this scenario as the Markovian system, which doesn't mean anything regarding Markovian of the past. It's just Markovian. Markov did many things. But the DAG here is if you assume Markovianity, and the joint probability distribution can be represented by the DAG in a way that this is going to be satisfied. This means that for every variable in my graph, such a variable is going to be independent of all the non-descendants given the parents. And then you have some interesting factorization. So let's see here. This is just the chain rule. So you know from basic statistics, you can get any order you want, and then the probability decomposes like the variable given the others, and then you get another one, and this is the chain rule. But once we start incorporating the independencies, because they follow like this, each variable is independent of the non-descendants given the parents. If you follow the topological order of such a graph, can be any graph, there's no causal reasoning here, then you can just stay with the parents here, and all the orders are going to be independent, so you leave them, you remove them from after the conditioning bar, and you end up with this distribution factorized like this. So in this case, we say that the probability satisfies the Markov condition. If you found such a graph that everything followed like this, is not always, but sometimes if the graph followed like a structural causal model and is acyclic, you get it. But then we call like this. And let's say like an example, if you have this graph, you can factorize, again, there's no causal semantics. This is just a Bayesian network. Then you can factorize. You get, I go a bit fast because this is not really important for the full lecture, but I want you to know that this factorization exists. And so I start with the chain rule. Then I start incorporating these independencies that I mentioned. So I will end up with just the parents after the conditioning bar. So W has just Z, Z has X and Y has just A, and A is alone. X is also A. And you follow like this. Yes, this is because I'm incorporating the independencies there. But you can also do the same when you have latent confounding. And this is what I wanted you to pay a little bit more attention, because that is the extension of Bayesian networks with latent confounding, which you probably have not seen before. And it's almost the same, but the parents now, there is this plus sign. So that's called extended parents. So it's the same factorization, but there is a plus. Okay. And what is this plus is a little bit complicated, so I go directly to the example, but then I can say that the probability satisfies the semi-Markov condition, which means it's just I'm not no longer in the causal sufficient scenario. I can have these bidirected edges here. And as long as I find a graph that satisfies such a factorization here, then it satisfies the semi-Markov condition. And in the example, it starts the same. So I get the joint distribution factorized by the chain rule. And when I started incorporating the independencies, and this independence I will teach you how to get later on, but you don't need from here. Basically, this is given from your distribution. You will see that after the conditioning bar, you get the topological order for such a graph. And you are going to have not only the parents, the directed parent, for example, the variable E, you have the D here, but you also have everything that's connected by a bidirected edge that came before in such a topological order, and the parents of such variable that's connected to the bidirected edge. So you're going to have the C and also the parent of C. So C and the parent of C, which is A. So I have the D, which is the real parent, then the variable connected by a bidirected edge, and then the parent of such a variable. And this factorizes. So you just need to remember now that there's a notion of extended parents. Once you know that, you will start understanding why there is an equivalence class of models that satisfies the same distribution, the same joint probability distribution. Let's get an example. The simple one, two variables, X and Y, and they are not independent of each other. So I start factorizing. So this is the only thing that I have no independence. So I can factorize. I can pick now one topological order, right? And it's the chain rule. So I can choose any order, and then I get Y given the others, and then the others. And this has a Bayesian network associated. Oh, this has a Bayesian network associated to it because it's Y has X as a parent and X has no parent. But I could choose other topological order. There's nothing prevents me to do that. And I can do the chain rule and now have, so maybe that one would be the easiest one to draw, but remembering that the extended parents exist, the first one could also be represented by this, because this is still Y, and the extended parents of Y, which is still X. And for the other one, you have Y, can be just directed edge, but you can also put the bidirected edge. And you can also have that because the bidirected edge is part of the extended parents. So you can draw many graphs where all satisfy the semi-Markov condition or Markov condition, and they all represent this probability of X and Y where there's no independence involved. So this forms something called Markov equivalence so they are all Markov equivalent networks, Bayesian networks, and they form a Markov equivalence class. So this is a very simple case with two variables, but let's see, and I can learn nothing from that. Correlation doesn't imply causation. There's nothing that I can learn from this, but I can go in another direction. So I have now one distribution where I observe one independence, and I have three variables. And I can do the same. I go a little bit faster. You see at home how this factorized, but you see in red that I'm applying the independence. So X is independent of Y given Z, so I can remove the X. And so I start with one topological order, I apply the chain rule, and then the independences. And then I get the Bayesian network. So it falls like this. I could also put some bidirected edges, and this still represents the same factorization and so on. But I can change the topological order and still apply because it's symmetric, right? So I can still apply some independences, some simplification, and I get a completely different graph, and so on. And now I ask, can I learn anything from this? So this forms the entire class of graphs that satisfies the joint distribution with one condition independence. Can I learn something from this? It's a bit hard to see, so I'll go a little bit faster. And you see that all the z variables, they are never a collider. Never. So I learned that z is always a non-collider in such models. So I don't need to know what's the true graph. I don't need to know the SEM. I just need to know that if I condition on z, I won't induce the Bergson paradox, for example. It's all good already. But I learned something. Let's go further. You go now with this distribution where x and y, same three variables, but now x and y are independent. And I do the same procedure. And now there is a pattern that's very interesting. Maybe you can see it, but I will also help you here. Now, all the models, they are a collider, all of them. So it's a very interesting signature that you have in the set of dependencies and independencies that leads you to learn something in the entire class. So I could say that I don't need a graph, but I could say that Z is a collider in the model, in the true model. I don't even need to know which model it is. And that's going to be one of the most important components in causal discovery. But before that, I promised that I would teach you how to extract such dependencies and independencies from the graph. And this is called a tool called disseparation. I think some of you said that you already know what is this. So, but I will try to give you a quick example. So the idea of condition is like, as I said, that these Bayesian networks are encoders of dependencies and independence, conditional dependencies and independencies. And there are a few triples or sets of three variables, graphs of three variables that explain pretty well the notion of this separation. The first is a fork. So a fork has Z here as a non-collider. And I put here obesity, age, and baldness. Not sure my example is the most fair here, but anyways, the age is basically explaining some correlation that exists between X and Y, some association between X and Y, because a person that's obese and bald is probably also old. Sorry, but yeah. Then basically, after observing the age of such a person, maybe this dependence is explained away. So after conditioning on age, X and Y are no longer dependent. So you have this pattern here. From this, I know that X is and Y, that is a path connecting both. So X is marginally dependent of Y, but after conditioning on Z, X is independent of Y. So this forms this pattern. A chain is similar. Z is still a non-collider here. And this is a case, for example, where maybe Y is a stroke, diabetes usually is correlated to a stroke. This doesn't need to have causal meaning, all right? But it's just a set of dependencies and independencies. But if I don't know if the person has diabetes or not, but I know that in her family, there are someone with diabetes, then the chance of this person having a stroke is high. But once I know if the person has no diabetes at all, doesn't matter the past, the person already is safe. So once I condition on the middle variable here on Z, X is independent of Y. And that is the same pattern. So that's two different graphs with the same signatures. But there is a different one where Z is a collider, or we sometimes call this V structure because forms a V here. But it's a simplistic scenario, but let's assume that the obesity here it depends on the diet and if the person performs some physical activity or not. And there's no correlation between X and Y here, which is not true, but let's keep this as the example. But you know that if you know that a person, so if you look at the diet and the physical activity, as I said, this is a simple example, you won't see any correlation. But as soon as I know if the person is obese or not, this gives me information. Imagine, for example, that I know that the person, I don't know, performs like a lot of exercises, run a marathon, whatever. But then the person is obese. How this can happen? Probably is getting very bad food, right? So it is not very good diet. So the fact that once I know that the person is obese, now I have information about the diet of the person. So two variables that were independent, once I observe if the person is obese or not, I have information about the diet. You know, so I create a spurious association by conditioning on the collider. And this also happens with descendants of the collider, because descendancies are just proxy. So imagine that I don't know if the person is obese or not, but the person is suffering from some heart disease. And again, it's a simple scenario where such heart disease comes from obesity. So I don't need to know that the person is obese. I can guess that the person is obese because of the heart disease. And again, I can guess what's the diet of the person because how it is deposited, right? So the point of bringing information can come from different sources. Doesn't need to be from cause factors. Can be from descendants, from conditioning on colliders, and that's very important to understand. And there is okay, so the signature is a bit different here. So that is a way to extract. Okay, those two are Markov equivalent models. I told you already, so this is a non-collider, and this forms a separate Markov equivalence class where z equals. So you look at the signatures. But that is a tool where I can extract some dependencies and dependencies based on the graph. And this is what the separation is about. And for understanding the separation, you need to know what are active and inactive triplets. So an inactive triplet, so we define based on the inactivity. So I take a triplet, this is VI, VM, and VJ, and is always inactive relative to a set, the set of variables that I'm observing is going to be such a set. And I want to know, here. So if the set that I'm talking about includes VM, and VM is a non-collider, which is there in Z, then the triplet is inactive. So it's the case of the non-collider. I'm observing the non-collider. So the non-collider is in Z, and and then the triplet is, so VM is in Z. So I'm observing VM, which is a non-collider, so that I make the triplet inactive. It's the case of the fork or the chain. It's also the case where I have bidirected edges now. So it doesn't matter how is non-collider forming, as long as there's no arrowheads two arrowheads pointing to the same variable in the middle, this is a non-collider. So in all these triplets, if I observe W, I remove the influence of X on Y or Y on X, right? So this path is now inactive. This triplet is inactive. There's the other case where now let's go here to the example where the middle variable, the W here, is a collider, and neither the collider, not even the descendants of such a collider, is in the set Z. So I cannot, if I don't condition or I don't observe the W, so W is not in the set Z, then the triplet is inactive as well. Okay, so as long as I don't touch on the colliders or on the descendants of colliders, these two variables remain, this triplet remains inactive. Now, this separation uses this fact because I can decide, let's go directly to the example here. So, for example, I can decide if X and Y are disseparated depending on the set Z, if all the paths that connect X and Y have at least one inactive triplet. So one inactive triplet makes the whole path inactive. So you just need one. And you can still have many paths between them. Let's stick with a simple example where there's only one, but you would need all the paths to be inactive. So in this example, the path includes two triplets, and the triplet is a non-collider. So I'm asking you here, what happened if the the set doesn't include any variables. So I still have this path, and the two triplets has a no collider. What happens with such a path? Is active or inactive? So you look at each triplet. So the first triplet, the middle variable is a non-collider. If I don't include the middle variable into the set, this path is active. I continue the path. The second triplet is the same thing. That is a non-collider. The non-collider is not in this empty set here. So this also is active. So the whole path is active. Once it's active, I say X is not disseparated from Y. So that's X. But if I include the B, now B was in the first triplet, then I make one triplet inactive, the whole path is inactive. So it's okay. The W is the other triplet, doesn't matter which one I'm talking about, so it still works. If I include both, doesn't matter. I still have inactivity. Now let's look at the other one. Now I have two colliders, and I'm asking the same thing. So this is the opposite scenario, right? So if I have a triplet and such a triplet has a collider, the triplet is already inactive unless the variable is part of the set. So I have two triplets, and these two triplets have a collider. So what's going on here? Don't know. With B, this is still good because I make this triplet active, but there is still an inactive triplet here. W is also the symmetric case, so I make this triplet active, but there is still one inactive triplet here. And then B and W together, now they make both triplets active. Okay? And the last scenario is a bit more complicated because now there are two paths. And this is an interesting case. Why? Let's see. So as I said, all the paths between X and Y must be inactive so that X is disseparated from Y. So let's take the empty set. If that is the empty set, what happened? I have this path down here, which has two active triplets, so it's not disseparated, right? Now I tell you, okay, let's put the B. What happened with the B? Now the path here is inactive because I make the first triplet inactive, but then there is this collider here through this other path. And once I include the B, I make this triplet active. So now the second path is active. So it's still not disseparated. Is there a way to make this disseparated? What about W? Who thinks that's yes? I would block this, right? What about the second path? The first one is not blocked. Yes, why? But but that's a collider. With a collider, this is inactive, but I'm adding W to the set. Just W. So there is one path that's X, B, Y. This is a collider. There is another path, X, B, W, and Y, which has no collider. If I add the W, yeah. Everyone agrees? Yeah. W is a descendant of B. Does this change anything? So conditioning or adding to the set, the descendant of the collider also makes the triplet active. is the case of the heart disease for the obesity. So observing a proxy or a descendant of the collider also makes the triplet active. So it's still no. It's a bit hard to see this one. Like you always have to remember of descendants of colliders, because this descendant, so it's a direct edge here, and the fact, so I don't want to, let's go back here, but you see, if you include the descendant of such a collider, this triplet is still active. It's just hard. It's tricky. Anyways, but that's an interesting situation because there is no way of separating X and Y, although they never have an edge between them. Which means because, so if the last scenario is just more complicated, but this is something special called inducing path. So X and Y, they can never be separated by just B and W. So you would always see a correlation between X and Y, although they don't have a directed edge. Okay, just keep this in mind. All right, but the idea is that would be a case where all the disseparations in the graph imply independences in the probability distribution. And yeah, all the separations correspond to that. And the semi-Markov condition that we saw before makes the other direction, where the probability distributions can be represented by a graph, and then you have the two sides. So the graph, a Bayesian network, represents all and only the dependencies and independencies in your graph, if you, of course, find a way to put all this together via this separation. And an interesting result from that also goes back to our example, but I think I forgot to add the example here, but we'll go back. But the idea is that for prediction, all that matters are variables that are associated to your outcome, right? And there is a notion called Markov blanket. And if you find the Markov blanket, you'll find the set that has the maximum performance in terms of prediction. So let's see what is this Markov blanket is. So in the case where the network is Markovian, or you are in the causal sufficiency, maybe you have heard about this. Basically, the Markov blanket includes the parents, the children, and the parents of the children. So let's see an example. If that's my outcome variable, okay, and I include in my model the parents, the children, and the parents of the children, what happens is the following. The parents are, of course, dependent, right? So there is a directed edge between them. The same happens with the children. So you cannot make them, so as long as they are dependent, they have information and they help you in predictive tasks. But once you include such a variable here, which is just a child, you are conditioning on a collider, and the parent of your children now becomes dependent, right? So such a variable here, again, if it's included in your model, is going to increase your accuracy. It's going to help you to have a better prediction of the variable V. But adding this one won't help you anymore, because you see, once you condition on this variable here, now you block such a path that's independent of V. So the variable is independent of everything that's not in the Markov blanket, given the Markov blanket. So if you want optimality in your predictive task, you are looking for the Markov blanket. And this doesn't have anything regarding to causality. Having a good predictive variable doesn't mean that it's directed, connected, not even a cause, right? And the same thing can be extended for semi-Markovian Bayesian networks, where you have the latent confounding. So it extends the notion for something called district. A district is basically every variable that's connected by a bidirected path. And basically the district plus the parents of the district forms the Markov blanket. So in an example, you see how far this can go. So I have my variable. This, imagine, is my outcome variable. I go there and include the parents. Let's see all the neighbors, the parents, the children, and now there's the spouses. Everything connected. But once I include such a variable that has a collider here, then another variable comes part of the Markov blanket. So it's helping my prediction. And this can go very far because everything that's connected by a bidirected path is part of it, plus the parent of it. So it can go forever if you have a lot of course, in practice, these dependencies may get weaker and weaker and weaker. You won't see it. But in terms of prediction, they are all helpful. And intervening on such a variable here doesn't give you anything, like you won't see an outcome, a change in the outcome because there's no causal path. So in terms of decision making, such a variable has no influence in the outcome, but it helps prediction. Got it? I think that's my plan for before the, yeah, well, I'm perfectly on time. Yes, and this is what I planned, and then later after the break, we will learn the equivalence class from data. Nice. Thanks. Okay, hope you have another bit of energy here. All right. So I think we already have the foundation for understanding how we start, how actually the Markov equivalence class or how parts of the causal graph can be recovered from only observational data. So one thing that we have to have in mind is that I will consider the non-parametric setting. So I don't want to make any assumptions regarding the types of the functions or the distributions of the exogenous variables. So it's the least set of assumptions that I will consider. Of course, with more assumptions, you could achieve something better, but here it's like I won't do any assumption that I don't need it. So, and I will only use observational data. So of course, if you had like knowledge or prior knowledge or other type of data, you could incorporate. But here is, again, is the least set of data, only the observational data, the minimal set of input and assumptions that I will consider. And in this scenario, causal discovery cannot learn the one graph that generated the data. Okay, there are some situations that with many assumptions you can get it, but here you cannot. So this is a identifiability issue. The only thing that we can learn is the representation of the Markov equivalence class. So all possible graphs are going to form a representation forming such a class that we call Markov equivalence class. And there are two types of algorithms. You can also have combinations of these two types of or paradigmas. One is a constraint-based and the other is score-based. One, we are going to, anyways, I will explain the next slide. And another thing that separates the field is if you are assuming causal sufficiency or not. So there are many algorithms out there that assumes causal sufficiency, assumes some other parametric forms, and then you can definitely go beyond the Markov equivalence class. But here I'm going to consider the insufficient scenario. So I won't assume that I have all the variables observed in my data set, so I can account for latent confounding. And I will explain this two set of algorithms. But with causal sufficiency, causal sufficiency, I said, is an assumption where all confounding variables have been observed. that is a bit strong, but has been widely employed to simplify both inference, discovery and inference. Okay, score-based acts like you do a search in the space of all graphs that exist. It's kind of, I mean, you could use enumeration, but of course it's not like this. You have strategies to search the space. But in the end, it's going to use some sort of goodness of fit of the full graph according to your data. And then you get the one that is mostly likely to generate from that. And the most common scores, I would say the most common score is the BIC that assumes that your system is linear Gaussian. In that situation, you have the BIC and it works either if you have all variables or not. So even under latent confounding, this is still a good score. But there are others, like for example, this one Bideau score for multinomial variables. It works if you are in the causal sufficiency setting, but there are other scores. Even when you have latent confounding, people are now developing more and more scores, but it's still the great majority is assuming Gaussian linear modules, and then you can use the BIC. Under causal sufficiency, there are like many algorithms. This started since, I would say, the GES, the grid equivalence search. But I mean, yeah, this is not I usually don't work on this setting, but this is just for you to know that if you assume causal sufficiency, I would say the score-based approach is the most reliable because you have this global score, and then it's easier to don't have like propagation of errors during the learning process. So it is a bit more robust when you have not many samples in your data set. Those are just the classical ones. But when you account for latent confounding, so it started more recent. So it was just after Richardson in 2022 that he characterized that actually under latent confounding, the Bayesian information criteria also works as a good score for causal discovery. And then a lot of people started developing these search algorithms. Most of them were grid search algorithms for learning MAGs. So I won't bring here what a MAG is, because I mean, it would have a lot of theory behind it. But usually you have a causal diagram, and then you have a way to represent many causal diagrams together as an ancestral graph, and that's a maximal ancestral graph. It's just a way to characterize many graphs together. And most of the algorithms, they learn how to learn a MAG, and a partial ancestral graph is a class of MAGs. It's all a lot of technical terms. You don't need to know all of this. You just need to know that at the end we'll learn a class, okay? But this is like a GS MAG because it's a grid search MAG algorithm, and it's one of the first that started. And I'm a big fan of this one because when I developed my algorithm, this was really hard to beat. This was like very good because it does a global optimal search. So it guarantees that you actually go through all possible MAGs in your data set using the BIC. So you still have to remember that your data has to come from a linear Gaussian model. And it uses this dynamic programming, the branch and bound algorithm. So it's fast, it's very nice. Anyways, I really recommend you, if you are in this scenario where you have linear Gaussian models, I would use this, okay? So it's guaranteed to find a globally optimal MAG. Right, oops, and there's another one here that's more recent, but anyways, people now started to like try to get, so you see, this is a very principled algorithm because it tried to do exact search. But of course, people are trying to scale. And scale is always dangerous here because once you scale, you make mistakes, and making mistakes destroy reliability of everything. So achieving scalability is very hard, but people are trying to get this differential discovery algorithms to, sometimes they make assumptions that the diagram now is both free. Both free means that if you have a latent confounding, you don't have the directed edge. So I started again making assumptions that, well, anyways, but once you put that, Also, they assume that it's a non-linear SEM with additive noise. So many people are now moving towards getting scalable algorithms, but this has a price. I'm not a big fan, but it depends on your goal. Very recently, we actually it's a great pleasure because it was a collaboration that started here in this school, by the way. But we published this paper for probabilistic causal discovery, which we also use the BIC for linear Gaussian models because it's one of the scores available, but you don't need. Basically, if you had any other scores, you can also use, but you use generative flow networks to sample several graphs that are also compatible with, like it's proportional to the BIC, so you can have the distribution of possible ancestral graphs. As I said, we are in the level of these maximal ancestral graphs. And then you can have a probabilistic view of causal discovery. So you don't learn only one graph, you learn many graphs, and you see how they differ according to the Bayesian information criteria. And this is very important because one of so when in practice, you don't have infinite data. And infinite data would lead you to the right BIC and the identifiability of the Markov equivalence class. But when you have limited data, you can basically have some false independences there, so or weak associations that you think that's independence, and then in the end the BIC changes, and of course you won't have the most likely graph for your data. Not necessarily is the true one. It can deviate. So probabilistic view of causal discovery has become very important because of the notion of uncertainty. So you don't have certainty when you have small sample size. And since it's probabilistic, we also used an idea of incorporating knowledge. And this is it's an active elicitation of knowledge, so the knowledge can be uncertain. So we did a way of asking what are the best orientations for certain edges. So once you learn the entire distribution just using data, you can start incorporating knowledge from an expert, and we did this optimal elicitation of the expert feedback. So it's a pretty nice result that you can see how unreliable can be depending on the sample size. And I would say this is still in the score-based scenario because it's based on the score. Another one another paradigm is called constraint-based because it's going to use condition independence tests. So as you saw in the first part, we have a map of these dependencies and independencies in the Bayesian network. So in the end, if you had a way to extract from data all dependencies and independencies that you have across all your variables, you would be able to put this together and find the best graph. And this is the idea of this algorithm. So the strategy is to align with all observed conditional dependencies and independencies in your data. And for that, you need something that's called condition dependence test. It's just a statistical test where you observe, you can assess the dependencies, or actually like the null hypothesis is the independency. So you can assess using a hypothesis testing if these two variables are independent of each other, giving a set of variables. Under causal sufficiency, again, that started a long time ago in the 90s with the inductive causation algorithm. At the same time, like 1 year after, but they actually developed independently. The PC is from Peter Clark. They developed the PC algorithm. Maybe you have heard about them. They're pretty famous, but they assume causal sufficiency. And the idea is that they start with a skeleton, and then they start applying these condition dependence tests. The skeleton is like the full set of edges. Then they apply the condition dependence tests and start cleaning the skeleton. Then they have a orientation phase. So this is kind of the idea of the first algorithm from the 90s. And this hasn't changed. It's always like this. You first clean your skeleton, then you apply some orientation rules. You see after a few slides how it works. I would say if you want to understand this basic strategy here, this is one of the interesting books from 2001. It's pretty old, but it gets a little bit of your notion, of the notion of this algorithm. But anyways, once you have latent confounding, the things change. And the first person to extend the PC algorithm was Spearts, and this was in 1905, where he developed the first version of the fast causal inference, or FCI algorithm. And after a few years, in 2008, Gigi Zhang, he proposed a few other orientation rules and proved that the algorithm is complete, which means that he found all the necessary rules to actually get to the equivalence class. So you cannot get better. It's a complete algorithm, and it even accounts for not only latent confounding, but also selection bias. And from that point, many people keep improving the FCI. So this shows how important is the FCI algorithm, in my opinion. Like the base is the foundational of causal discovery. But of course, there are some limitations, and people have been improving from a long time. So it started with the anytime FCI, then the CFCI, and so on. Even myself, I have this paper called Data Compatible FCI, where we model uncertainty, but people continue working on this, especially like extending to different scenarios. So for example, there are extensions to time series data. Klassen also and Mui, they recently proved that the FCI algorithm also works if you have cycles. The only thing is that they won't show you the cycle in the graph, but they are going to be robust if the cycle exists. So they have been working a lot in the extension of to account for cyclic mechanisms in causal discovery. So it's a very important extension, and the FCI is just still there. So let's see then how causal discovery in constraint-based paradigm works. So you always start with the data, whatever data set you have, with any variables you have there. And I can say that because you can have latent confounding. So it doesn't matter the data sets that you have in hand. And as I mentioned, there are many multiple structural causal models that could generate the data, but this is in red because I won't try to find those. It's impossible. Actually, what I'm going to try to do then is to identify for all pairs of variables, and here is just 3 variables. It's a pretty simple scenario, but in 3 variables, I can tell you that the only independence that exists is that X is independent of Y, and everything else is dependent. So I can basically run all my tests over all my variables. That is a better strategy to not do exhaustive testing. But once you have the list of conditional dependencies and independencies, then it's straightforward. Like basically, I mean, this you already saw, like you could enumerate, this is not how the algorithm works, but you could enumerate all the possibilities. What the algorithm does is try to identify the invariances across all the methods. So this we saw from in the beginning of the lecture. You saw that the only invariance that exists is this the fact that Z is a collider. And what causal discovery is going to do, and it's a complete algorithm, is going to recover all invariances. So in the end, for example, the FCI algorithm is going to learn such invariance and have a representation where everything that's not a circle is an invariance in the class. So you see that there's 2 arrowheads pointing to Z because this happens in all the modules in my class. But the circle means that this could change. If you go back a little bit here, or here, I do. So if you go back, you see that some of them start with a tail, others starts with an arrowhead. So there's no invariance in the X side. There is also no invariance in the Y side. Sometimes it's an arrowhead, sometimes it's a tail, sometimes it's both. So that's why you learn that it's a circle. So it's not that the algorithm could learn and it was not and he didn't learn it. It's actually that's the class has both. The class includes both models, the one with the arrowhead and also with the tail. So it's informative. It says that it's a non-invariance. And this is a complete representation of the entire Markov equivalence class, and we call this graph as partial ancestral graph. So the most important paper, if you want to understand how the algorithm works, is the original paper by Gigi Zhang, where he proved the completeness. The proof of all the rules are pretty simple. It's all based on logic. So I'm pretty sure that all of you can learn after watching this lecture. Yeah, so that's also something in terms of ancestral relationships. So remember, everything is a kinship relationship. So we lose the idea of directness. So if I have an arrow here between Z and Y, doesn't mean that there is an arrow in every model, only means that there is an inducing path that could not be separated, but Z is always a known ancestor of Y. So you need to remember that there's like such long paths that could never be separated. So in the end, an edge here is just an inducing path. But the idea of existing a causal path means it's ancestral relationship. And the idea that doesn't exist as a causal path is the idea of non-ancestral relationship. So this is still faithful. Okay, let's see how it works. So imagine that this is my causal diagram. It's in gray because I won't use this, right? This is just for us to follow. So this is unknown. From this causal diagram, now that you learned this separation, you know all the dependencies and independencies that's implied from that. So you can verify the only independencies that exist is that X is independent of W and X is independent of Y given Z and W. Everything else is dependence. Anyways, this is a graph, and this implies this set of dependencies. This has causal meaning, but you won't know. So this is all unknown. And how the algorithm works is like you start with the complete graph. Why the complete graph? Because this is the parameterization of all possible graphs in the world over those 4 variables. You could have everything there. So it's all circles. However, once you start assessing independencies in your data, you learn that these are exactly the set of independencies that you have. Now, big attention here. That's a pretty big assumption that my data faithfully recovers the exact set of dependencies and independencies. And this is pretty strong. If you make a mistake here, everything is going to make a mistake. It's going to be wrong. But let's assume for now that this is the case. So you have like enough sample size, you have a good condition dependence test, and it could recover perfectly that this is exactly the independencies that you have in your data. Once you have that, then you start cleaning the skeleton. As I said, there's always a skeleton phase and an orientation phase. In the skeleton phase, you clean up everything that you found as an independence because you could explain away, right? So the fact that X is independent of W allows you to remove the edge between X and W. The fact that X is independent of Y, doesn't matter the conditioning set, means that X and Y are not directly connected. It's explained away, right? So there is a way to explain, for example, X is dependent of Y marginally, and this is still represented by this long path, but the fact that they are independent for given some conditioning sets allows you to remove the edge. Then it comes a set of rules. And the set of rules are the R0. The R0 is separated for not sure why. I think because of the PC algorithm, that's the simplest rule. But then there's another set of 10 rules, so 11 rules in total, that you apply basically in any order you want. As long as you can apply, you continue applying until you cannot apply anymore. And then at the end, you have the full directed, the partial ancestor graph with all edges that you can orient. And basically, it's a complete algorithm. So if there's something that could not be oriented, it's not your fault. It's actually because there is no invariance in the class. How you learn, how you interpret this graph, there is a green error here because this is called visible error. And this is important because it tells you that this edge is not confounded. So let's go back to the graph here and see if this matches. So this class includes this graph. Why? First, because I can have, for example, the directed edge here is part of this right? You can basically replace the circle with a tail or with whatever, but this is the case a tail. The edge between W and Y represents that exists a causal path from W to Y, and this is the case. As I said, you lose the directness, but every time that there is a causal path and this is recovered or this is invariance in the class, you find a way to represent, and this is going to be, in the case here, you see there's no way to separate W and Y, and then that's why there is an edge, but this is representing the ancestral relationship from W to Y. And the green edge is that this edge is not only a causal path, but there is no confounding. So you see there is a confounder here, which is no longer represented here. This is all good, that's no problem, but I know that's not visible. So there is no green because it could be both, could be an ancestral relationship and a confounding together. But I'm sure that in this case here, there's no confounding. So it's very powerful. Not only the direction I learned, but I learned that there's no confounder that could, so this is the first step for identifiability of the edge, of the causal effect. All right, so that is something that's an extension of the separation, which you can learn in the paper by Gigi Zhang, which is called M separation, because here is no longer from a directed acyclic graph, it's from a maximal ancestor graph, it's MEG, but it's a M separation too, is exactly the same, and you can use such criteria to determine what's the set of dependencies and independencies that come from the entire class. And the entire class, not only this graph, but all the other graphs represented by this class, has exactly the same set of dependencies and independencies implied. So you cannot go further, you cannot refine the class because that's the only information that you can extract from the data. If for any other reason you say, I know I have prior knowledge, you can, for example, remove the circle here and put a directed, you can go further. But then it's no longer just the set of dependencies and independencies that the equivalence class is representing. It's this plus the knowledge. But this is, as I said, is a complete algorithm, and then it's representing the entire class of diagrams. Here you can see in this example, there is no selection bias, but if you had selection bias, what is selection bias? Imagine that you collect data from a children's hospital. So basically there's just kids in your sample. And it is possible that the fact that you collected data just for kids leads to some selection bias. So two variables can be, so imagine that's a hospital for kids that have some chronic disease, whatever. Then the fact that people are going to such a hospital because of the age and because of the chronic disease is like the reason why you selected the sample as well, because you just selected sample for such a hospital. So you are conditioning on a collider. The hospital is a collider, then you have age pointing to the collider, also you have the disease pointing to the collider, and you're conditioning on it because you just have data from such a hospital. And conditioning on the collider leads to associations. So some associations can only exist because of selection bias, and the algorithm also can recover. And in such a case, it's going to be appeared as an undirected edge. So if you have a peg in the end that is undirected edge, it's because there is a hidden variable that's creating selection bias, and you just cannot recover if you don't know and go and collect more data to have the entire scope of the variable. Questions to this point? Okay. So yeah, this is just an interpretation of this, but I think you all got it. Let's go a little bit into the rules. I think it's fair enough to understand how those rules work. As I said, the rule 0 is the easiest. The rule 0 says that if you have a triplet and such a triplet is unshielded, unshielded means that the V1 and V3 are not directly connected. So this is a case, V1 and V3. And the V2 is not part of the separating set between these three, this 1 and 3, then it's for sure a collider. Because, so you have an edge between V1 and V2, you have an edge between V2 and V3, but V1 is independent of V3 without conditioning on the collider. And you remember that this is a case that only happens if this is a collider. If it was a non-collider, you would have to condition on V2 to have the separation. Since you didn't, it's because it's a collider. So you learn a collider. And this is what happened in our example. We started with the skeleton here, and the rule 0 starts with, so I have X is independent of W, where Z, so X and W, so that is a triplet, and Z here was not part of the separating set because it's independent marginally. So the fact that it's not part makes Z automatically a collider. Now, that is the other edge here. So between X, Z, and Y, so there is this triplet here. So the independence between X and Y does include, so Z is part of the separating set. So you see that Z is here together with W, but Z is part of the separating set, which means that this is a non-collider. So I go, oops, so I don't do anything. Basically, I don't include as a collider. So this I leave as it is. But then you automatically know, which is going to come next to the next slide. If this is a non-collider, what leaves you is obviously a tail, right? So you have here the case that if you have such a triplet, since you know from before that this is an arrowhead and this is an unshielded triplet, since you know already that you compute all the rule 0, oh, now I know because rule 0 is separate, because you have to apply the rule 0 every time, and then you start applying the other. So you have to fully complete the application of rule 0. So here you know from before that this was not a collider because you applied exhaustively the rule 0. So since this is not a collider, can only be a directed edge. So you learn a cause. And this is what happened here. I just said that we didn't do anything, but now we applied the rule 1. And this was like this before. And now we automatically have a causal direction. There is another bit more complicated rule. As I said, there are 11 rules in total. I won't go through them. If you are interested, you can read the paper, but this is an important one. This is a generalization of the collider rule, which is the 0, where it's just a more complicated ways, right? So here, there is a path that's called discriminating path, but intuitively, I will explain, basically, that's a path that's formed only by bidirected edges, except the last. So that is this path from V1, 2, 3, 4, and 5. Everything in the beginning is a bidirected, it has like a collider in the middle, except the first, right? But the second is a collider, the third is a collider, and I'm sure, and then the other, every collider variable in this path is also directed connected to the last as a non-collider here, which is ancestor relationship. So V2 is ancestor of V5, and V3 is ancestor of V5. So this part was learned. It's already learned. Assume that from before applying the rules, this is learned. So what happened here? When you have the independence between V1 and V5, and they are independent because they are not connected. So the independence between V1 and V5 for sure included V2 because of this path. But when you include V2, this opens this collider part. So for sure also included V3. And when you get to the last variable, there is only 2 possibilities. Either V4 is in the separating set or not. And you again discriminates exactly as you discriminated the collider rule. Because if it is part of the separating set, then it's a non-collider and you automatically can orient like this. This is an ancestor relationship. There is a bit more involved proof to say that this is directed, but this starts as a non-collider, and then because there's no cycles and stuff, then you basically know that this can only be ancestor relationship. But if this V4 was not part of the separating set, then for sure it was a collider. So you would orient this into 2 arrowheads. So it's the collider, the same collider rule, but it's because it's a little bit longer, we call it the generalization of the collider rule. It's just another And this appeared in our example. So we were in this situation here, right? And X is independent. So that is this path. It's a very small discriminating path, but the W is a discriminate, like the path X, Z, W, and Y is a path where everything between the first and the second to the last variable is a collider, it's just one. But this is a collider, and such a collider is ancestor to the last. So this path, X, Z, W, and Y, is a discriminating path for W. So if W is part of the separating set, for sure is a non-collider. If it was not part, then would be a collider. And in this case, it is part of the separating set. So I can orient like this. Right? So those are like logical rules that's just based on the fact that you already covered all the colliders. And then everything else is based on if it's not a collider, then sometimes it's automatically directed. And also it's not forming any cycles, or that is something that maybe you read the paper, there's something that's also, we cannot, for this undirected edges, you also cannot have almost cycles anyways, but that's a bit more complicated. But this is a case where you clearly see that you can just direct the edges, orient the edges because of collider rules. And the rule one is also simple. That's the end. Is there any question here for that? It's a bit complicated, I know, but I think it's important for you to know that those rules are not magical. They are just logical rules, okay? But of course, they are all dependent on your test is being correctly determined. So this is pretty important. So a PEG, as I said, represents the entire Markov equivalence class, and this was the PEG that we learned. Just for you to have an idea of the possibility of graphs that are part of this graph. So any graph where Z is a non-ancestor of X and W, and W is an ancestor of Y, I mean, there are also the independencies involved, but you see that you can construct many graphs following this. So there are many of them that you have, for example, here X could change, right? The side of X can change, but Z is always a collider, Z is always a collider, Z is always a collider in this path here. But in the path of X, Z, Y, they are all equal. You can never construct a model where this would not happen. The fact that W is an ancestor of Y, but it's not visible, can be in different ways. So it can be directed edge, can be bidirected, but then you need a directed path here. Here you don't need a directed path because it's already represented here, but you can have both, right? So there are many ways to represent the ancestrality of W and Y, and since it allows to be confounded, I also can incorporate some confounding variables here. So there are many graphs involved that could have generated your data with the same conditional dependencies and independencies. That's the best you can recover. That's complete. Okay? Yeah, and via M separation or M separation here or this separation here, you would see that they all have the same set of dependencies and independencies. They are all equivalent. Yeah, that's the true one that you'll remember from that. All right, so those are just another examples where very simple examples. So collider one, you'd be like this. Just a non-collider is all circles, but this has meaning, like because it's a non-collider in an unshielded triplet, I know that this is a non-collider, right? So although it's all circles, I know that this is a non-collider, it's a definite non-collider. This, you cannot learn much from this side, but you can determine that X is a cause of Y and also visible. This one here, you can basically learn that there is just a spurious association between Z and W. This is just the example, it's a different example of the same Markov equivalence class. Okay. And implementation of the FCI is everywhere since it's like very, I mean, it's a kind of old and one of the most important algorithms. You can have all flavors. You have R packets, Python packets. Yeah, and I would like to show you a little bit of how a condition independence test works, because I've been working a lot on this direction, and I think like it's interesting that a computer science task at the end is just a statistical task, because it's just developing well a condition independence test. So, and it's also something that you don't blindly apply. You need to know what's the best condition dependence test for your data set, because if your data set is Gaussian, then you apply some condition dependence tests. And this is what I'm saying here. So if your all observations are independent, so IID data, and then your data is Gaussian, okay, you can go there and apply the partial correlation test. But if you have different types of data in your data set, you have binary, continuous, multinomial, then maybe you are okay with linear modules, then you can choose. There's like, for example, this other one that's based on a likelihood ratio test and generalized linear modules, and it's okay. But you see, you are starting making assumptions here to fit your data. But then you say, no, I don't want any assumptions. I want the most general algorithm ever. Okay, so maybe you can go to kernel-based non-parametric tests, but then it requires more samples, and then requires more computation, and you need a lot. So, but it's a good choice, and it's a very important choice here, because if you have one mistake in this test, everything gets wrong. Yeah, so those are just a few. There are many algorithms, tests out there, and they're not that hard to develop, right? So Fisher partial correlation test is for Gaussian variables and assumes oh, yeah, and assume this is was developed more than 100 years ago, and is one of the most important even today. And it's basically assume, like this is your test, so it's a hypothesis test, right? So you imagine that you want to test that X is independent of Y, given a set S. How you do it? Yeah, remember, you're assuming multivariate Gaussian variables. So how you do it, you get the partial correlation coefficient, and you for that, you just need two linear regressions. One, okay, you assume that all is IID. One is a linear regression here, where you fit X into, and you use as predictor the set S. So basically, you have a regression for X just using S. And then your error term here can be computed. I mean, this is just explaining the equations, but you're going to have two regressions, one for X given S and one for Y given S. And then the partial correlation coefficient is just the correlation of these two error terms. What is the intuition behind it? The intuition is like, I get X and I explain all the information from X that's in S. And in the error term is everything that could not be explained by S. And you do the same for Y. I get a linear regression, and I explain everything that I can using this equation. So all the information from Y that's explained by S is not going to be in the error term. But everything that's left in the error terms, if they are correlated, this means that both X and Y, they were associated even though I accounted for the information on S. It's pretty intuitive, right? So, and then of course, this is assuming Gaussianity and all of this. And then if you basically compute the correlation, you can do the test. The test is in the next part. So the significance of the partial correlation coefficient. So you have the null hypothesis for the independence, and the alternative hypothesis is the dependency. So if the correlation, if exists correlation between the residuals, no, sorry, if the partial correlation coefficient is 0, means independence. If it's non-zero, is dependence, is the alternative hypothesis. And basically, you get these statistics. It's just a transformation, but such a statistic, it follows under the null hypothesis. It follows a standard Gaussian distribution. So you can test against the null distribution, and then get the p-value and so on. So it's pretty straightforward. Like you get if the correlation is significant, then it means that the variables are dependent given the conditioning set. All right, but it's assuming Gaussianity, right? So how can we accommodate then heterogeneous data types? So it's not that hard. Maybe you can use generalized linear models. Generalized linear models, you can now, instead of having common linear regression, Gaussian linear regression, you can now fit the right distribution using the link function for each variable type you have. And one of the most easy way to do that is the likelihood ratio test, where, again, let's assume now that x and y, I want to test if x is independent of y given s. And I have to choose an order. So basically, I want to try this order first. So the independence is the independence of y and x given s can be written like that, right? So if x is independent of y, it's no longer part of here. But I chose y to be on the left side of the conditioning bar. And when I chose that, I can now fit two models, again, assuming IID data and all of that. But one of the model is the model where y just include the set S. So that's the null model, assuming independence. So that's the model under the null hypothesis. So there's no x, it's just the S set here. But then I also have the alternative model where x is part of it. So now I have two competitive models. And if they are different, significantly different, what does this mean? That x is still bringing information to my variable y, even though s was accounted for. And you can compare two equations that are nested by something called likelihood ratio test. And that's how it does. And you see that you can account for different types of variables using generalized linear models. So see, linear models are very relevant today. And yeah, that's one thing. Of course, I can choose the other direct. Oh, sorry, no, here's the significance, how you compare or how you compute the statistics for the likelihood ratio test. So basically, you can get the log likelihood of each of the equations, and then you compute the log likelihood test statistic. This statistics is just -2 of this. And then this, so this has a distribution. So under the null hypothesis, this is a distribution that follows a chi-square distribution with k being the dimensional of your number of parameters. This is a chi-square distribution, and you can test against it with the degrees of freedom. So this enables you to test this order. So you see, I chose y to be on the left side to be my outcome variable in the regression. But since it's symmetric, I could also flip. So I can switch the rows of x and y, and now they do the test on the other side just to get a feeling if something is changing. But then I can follow everything, get the p-value of everything. And in theory, they should be symmetric. They should, but in practice, it's not, because you have issues of sample size and anything. And then there are several heuristics to say, well, how can I combine both p-values? So sometimes they say, okay, but let's get the minimum, others get minimum favors dependencies, the maximum favor independencies. So it starts getting a little bit heuristic. But anyways, there's a paper that proposed this weird equation here. And they're in a heuristic way, they show that control well the false positives and false negatives. Anyways, that's a paper. Now you start asking yourself, oh, sorry, this is just the package if you are interested. So most of these tools, since it comes back to now have a statistical approach, it's going to be more available in R, but more and more people are moving this to Python. Yeah, so see, this is just a result that only under joint Gaussianity, or like if the full distribution is Gaussian, so we have a multivariate Gaussian distribution, everything is the same, right? So zero partial correlation corresponds to no improvement in the model fit, and also improves no statistical significance if you just do regression analysis. So only if you have a linear Gaussian model, these are equivalent. But if you, for example, no longer are in the Gaussian situation, then you have to go to likelihood ratio tests or F-tests and so on. Okay, this is just a result. But now you start asking, this is kind of weird as well, right? Because we always learned that hypothesis tests You can decide about rejecting the null hypothesis, but you can never accept the null hypothesis. And here I want to do both. I want to say what is dependent and what is independent. So what people do, or at least did in the past, and usually you get like a significance level, as in hypothesis tests, let's say 5%. I'm not even telling you the problem of multiple comparisons here. But let's pick one. And then what in causal discovery people do say, if my p-value is lower than the significance level, I will say, this is dependent. So I'm rejecting the null hypothesis. So until here is all good. But they also said that. And, oh my God, if your statistician sees that, they are going to cry. They say, oh my God, this is not possible, right? So you cannot say if you don't reject the null hypothesis, you are accepting the null hypothesis. So it's all wrong, right? In a statistical point of view. But causal discovery, you remember that you were not using data. They were assuming that you have the perfect list of dependencies and independence. So they are not wrong. But the point that you introduce data to estimate the dependencies and independence, and then we're now in a statistical problem. And so basically, even when the condition dependencies are correctly specified, you can still have problems of limited sample size, weak effect sizes, multi-collinearity if you are the linear models. There's so many problems. And this consequences basically says that failure to reject the null hypothesis are false independencies, right? And incorrect rejection of this are going to be false dependent. So you can have mistakes here. So how you deal with that? So this is what I've been working and a lot on this. And what I did here is this basically modeling the uncertainty in these condition dependence tests and moving a little bit towards Bayesian inference, right? Because in Bayesian analysis, you can basically have you can quantify the evidence towards the null hypothesis and also towards the alternative hypothesis. So basically, I developed like a score where I assess uncertainty in all these condition dependence tests, and then I have a global score. And I incorporated such a score in the development of in the procedure of the FCI algorithm. So every time that I say, is this a dependency or is it independence? Now I bring sometimes both possibilities if they have uncertainty. And this comes to like also a grid algorithm, but I also have in the end multiple partial ancestral graphs that because of uncertainty in these tests. And in the end, I won't have just one. I will have a list of possible graphs, each of them with a score. And then you can decide later on if you had a good certainty in your tests and you can trust on this, or you should there go back and collect more data. And now it's the part that more data, the better, because you are doing the proper way and your problem reduced to a statistical problem where more data matters, right? So it was impressive how improved the robustness in limited data sizes. And when I say limited data sizes, is crazy. Like sometimes here you are seeing 4 variables. I would get faithfulness, which is all correct without modeling uncertainty, if you have like 10,000 samples. In practice, this is pretty big. Like for machine learning, this is not too many, but in many situations for medicine, this is impossible. So if you don't account for uncertainty, you end up with the wrong one, almost certainly. All right, and as I said, another alternative to account for uncertainty for this was this probabilistic causal discovery, and you need a score. Maybe we can consider extending this paper now with the score that I proposed for the DCFCI paper, but we could also like use the scores available, and the one that we used was the BIC, and what we did here was using a generative flow network to sample the graphs. And the graph is an ancestral graph, and we could score them using the BIC because we just used linear Gaussian models. And the interesting part is that you get the distribution. So once you learned the distribution, you can start asking the expert. Now that I have like the circle things, I can ask, what would be the relationship between this pair of variables? Maybe you know, maybe you not. If you know, you can bring the information, and this, you update the distribution in a way that you can go beyond the Markov equivalence class now because you're incorporating prior knowledge. But the idea is that first you learn the distribution, and the distribution now is not one graph. You have the whole graph of all possible orientations based on a score. And then you update this using this optimal strategy for eliciting feedback. So it's kind of a causal experimental design thing, because sometimes you have access to the information via experiments or via observation, and then you can keep asking what's the best one to perform to, in the next iteration, improve your causal discovery. And this can be uncertain and the probabilistic knowledge, right? All right. Then there's also another strategy to incorporate more samples in your data. And if you're interested, you can go to the poster session. This is the student that I have. He's been working on federated causal discovery, because you can also collect multiple data sets together. And not necessarily these data sets, they have the same set of variables, but sometimes in the overlapping, it's good to have more samples, and this helps in the faithfulness situation. And then he did this in all federated way, so you can have like so you can learn the condition, you can test the condition dependencies in locally, and just transfer the p-values, or no, sorry, this is meta-analysis, but you can also do in a completely federated learning way. You can just transfer the coefficients. Here was based on linear regression, so you can learn like the full model by just transferring the parameters. And then in the end, you learn not only the local models, you can combine this. So for example, the first data set here was ABCE, the other was ACED. And you see that alone, the data set over these 4 variables alone could not learn that C is a cause of D, because you don't have C and D together. And here, even though you have C and D together, this is not enough to learn that C is a cause of D. So putting together, you learn even more than just what you learned separately. So because you constrain the scenario, you can get much more information by combining multiple data sets in this way. So yeah, so basically he did this by computing the condition dependence tests in a federated and privacy preserving way. And we accounted for all these possibilities of, so we have latent confound, since it's based on it's like an extension of the FCI algorithm for multiple data sets. You can account for latent confounding, selection bias. The data sets, they can be heterogeneous, so you can have like a site effect. So the sets of variables can be non-identical. He used the likelihood ratio test that I just mentioned to you to account for different data types. So it's pretty general, and you can maybe improve faithfulness by doing that, because then you have more samples. Yeah. All right. And the last thing that I wanted to bring here in this lecture is the next step, right? Because I told you the classical pipeline is started with a graph for what? For identifying the causal effect. And then I mentioned that the pipeline was extended by replacing the causal diagram with a partial ancestor graph, which you just learned how you do it. But now we need to do the next step, which is effect identification, both from a causal diagram, because you need to know how to do this first, and then also from a partial ancestral graph. And then this completes the full pipeline of how to do causal effect identification in a fully data-driven way. Right, so that's the pipeline I mentioned. You can have the causal diagram in the beginning, and then the second step is what we are going to see now, the causal effect identification. And then the estimations just plug in here some estimators. All right, so what is identification of the effect? First, we need to understand what is this. It has the same flavor as before, right? So before, I wanted to find invariances in the full class, and only things that are invariant I could recover and put in the representation of the partial ancestral graph. Here's the same. I can only identify the effect if I know so I know the graph. The graph can be the causal diagram or the peg, it doesn't matter, but I know the graph, and that is like a space of all models that agree with the graph. There are many models fully structure causal diagrams, structure causal models that have the same structure. They are in the blue here. But also I know the probability distribution. This is given, right? I'm assuming either through data, but you have the joint probability distribution over the observed variables. And that is then the intersection of those, so that agree with the structure and agree with the probability distribution. If all models in the intersection, they agree on the causal effect, all of them have to agree on this. If they all agree, then I have effect identifiability. If you have at least one model there where the effect changes, then you won't compute it. It's the case where we have a hidden confounder, like a directed edge together with the confounder. Like the case of the doctor that was just prescribing to health people drug. If you don't have it, you won't have identifiability because you have the model where the doctor is there. The model doesn't know where the doctor is, what the doctor does. So you won't have identifiability. So, but if you have a way to clean up everything and make sure that the effect is all together in all models that agree with the structure and agree with the distribution, then you will be able to recover this effect. Okay. The easiest case is called backdoor criterion. It's the easiest. Why is the easiest? Let's see how it works. I like to go to the example and then we go back. Maybe my example is too far. Anyways, but you have like this graph. And then let's see here. So I want to find the causal effect of X on Y. Is this edge here? But I have something creating association between X and Y because this path, we just learned that since those are non-colliders, this is active. And then the association between X and Y then is due to this edge plus this other path. So it's the composition of both. So the first thing that I want to do then is create this graph where I remove all the directed or the causal paths. So what's going on? Yeah, so here. So I remove this and then I'm just looking at the paths that create confounding. They are called backdoor paths because they come here into X, maybe in the backdoor, and then here's in the backdoor, and it's called backdoor because it's into X and also into Y. This create a backdoor path, and this graph X bar removes everything that's not a backdoor path. So at the end, you have the graph only with the backdoor path. And then I want to find a set Z that this separates X and Y is in bold because I could have multiple X and Y, but here's just one variable. But in that graph, so I want just to block such confounding path. How do I do that? So we just learned the separation, right? So just Z equals to Z1 is making this triplet inactive. So the whole path is inactive. So just Z1 is enough to cut the flow of information here. If I use both, it's all good as well, right? All right, but let's imagine that this is my graph now. That's not so simple. So I have two paths, actually many paths between X and Y. So I had this X1 and X2. And now I have this other one through here. So my question is Z1 is 2 enough? No. So Z1, if I put Z1 here, what happened? That is this collider that's open. This one is open. But which path then is open? Because this is closed. This is closed. This is now open. This is okay, but this is closed. This one is blocked because I condition on Z1. This is also, the full path is blocked. So this path is fine. This path is fine. And this path is fine. So actually continues working. But, and Z1 is Z2. Z1, it's kind of similar. But what about Z1 and Z3? If I use Z1 and Z3, now it gets a problem because that collider that we open no longer have Z3 to protect. So we open this triplet, or we make this triplet active. This triplet is active, and now it's a non-collider continuous active. So it's a bit complicated sometimes to find the set, but Z1 and Z3 doesn't work. What about Z1, Z2, and Z3? There is now this other path here that's fully bidirected that you also kept open. So although it's more complicated, just Z1 or just Z1 and Z2, oops, should be Z2, but they continue working, right? And the criteria is that, so if you find a set Z that this separates X and Y after cutting the outgoing arrows from X, then you have, and this set Z doesn't include descendants of X. So there's no descendant here, so it's a simple case, but this is something that you have to take care of. The set Z cannot have a descendant of the variable X. Then you are in a situation where Z, for sure, gives exactly that expression that we saw in the example in the beginning, where Z can be either Z1 or Z1 and Z2. So you find exactly the set Z that satisfies the backdoor criteria, and then you can include this to estimate the causal effect. Hard? I mean, as I said, this separation is all you need, but this separation is very tricky. So, but it's nothing here. It's just finding, of course, there are tools to find this for you, right? So you can basically ask, is this set satisfying the backdoor criteria? And then it's going to do all the separation for you. But that's important for you to know that adding all the variables that you have in the data set may just hurt you. Like this is a case where all the variables Z1, Z2, and Z3 is inducing more bias than cleaning bias. So without having this understanding, you cannot get the causal effect. And okay, and then you have to be careful with what's out there as a propensity score estimator for causal effect. Because what many people tell you is that this is a way to estimate the causal effect, but they don't tell you that they assume that Z is already satisfying the backdoor adjustment. So who have heard about the propensity score approach here? Yeah. So such method doesn't tell you how to, that you need to choose the set Z first. It's just say, just get whatever you have it. And in this example, Z cannot be Z1, Z2, and Z3. It has to be either or Z1 or Z1 and Z2. Otherwise, you're going to actually have a bias. But anyways, assuming now that you properly found the set Z, and there are some data-driven ways of finding it, you don't need the graph. But here, let's assume that you had the graph and you found correctly the set Z. What you can do in this propensity score approach is like this expression that's now an estimation. So you see, they started with the formula. It's like they skipped the part of effect identification from the graph, assuming that this is the right formula, but it requires the right Z here. But once you have this formula, you can just do some trick here, algebraic trick. So you basically multiply by the same quantity here. And now the part on top is the joint. The part on the denominator is something that we call propensity score, because it's the propensity of receiving the treatment given the set of covariates. And then you write like this, and then you have a very nice way of estimating the causal effect via machine learning, because the denominator is just a conditional probability distribution. And when Z is very high dimensional, you can use whatever technique you have in hands. However, remember, this only works when Z is satisfying the backdoor criterion. Yeah. And it's very nice also, the idea of this, how this works, because what they are actually doing is creating something that we call pseudo-interventional samples. When you have this propensity score approach, what you are doing is the following. So you imagine that you have such a graph, and Z here is a very big Z, because I'm putting in the notation that Z can be like a very big variable, and this is called cluster causal diagram. But basically, Z satisfies the backdoor adjustment for X and Y. But the propensity of X is different than the propensity of X. So sorry, the probability of X is different than the probability of Y given Z, because you have this error. So X is not randomized. Remember in the randomized experiment, to get rid of the confounding path, you just randomize the assignment of the treatment. But here is not. You have a propensity to receive the treatment that depends on Z. And then this is what you do then is that you reweight the samples by multiplying each of your observations by 1 over probability of X and Z. And when you do that, you basically get rid of the X here. Let's see an example. Suppose that you have, this is your original sample, and then it's biased, right? So for example, I have the Z as a color, and those are just my quantities. So in my group, my control group is biased. I have more green than blue. And here in the treated group, I have more blue than green. But then I get those, it's like I have 1/4 of blue, 2/3 of green, and so on. This is my probability of X given Z. If I multiply by the inverse of the propensity score, then I do something like balancing. And now I have exactly the same proportion in both. So this creates something called pseudo-interventional sample. And after reweighting, I can act as this came from a randomized experimental study. And that's why we can do exactly this. We get a sample, then we reweight, like for every sample, I do this, I multiply by 1 over the propensity score. And this, and then this gives me exactly the expectation of my do X. So it's pretty simple, and people are working on this intensively by finding very smart ways of computing this propensity score, but they are not always careful to find the correct Z. So you never have to skip this step. All right. So, but backdoor is not always what you have in your scenario, right? And once you understand that the backdoor is just one scenario, you will start actually thinking about what happens if I'm not there. And this complicates the stuff. For example, this graph, you would not be able to solve the effect of X on Y via backdoor because you have a hidden confounder right here. So you could never block this path. However, there is still a way of finding the effect of X on Y if you have a mediator, and such a mediator is not confounded. And I won't go through the derivation of this. You basically use the calculus and you find a way to get to the expression. But for a different graph, you have a different formula and gets a little bit more complicated. Also, if you have a little bit more complicated, that makes now so you see this is just a bidirected edge, but now I have a Z creating a confounding, and you cannot just ignore this because you have a confounder between the mediator. So you have to first get rid of the confounder between the mediator and the outcome, and also between the treatment, to then apply the front door. Now it's called conditional front door. So it's a different formula. And you keep changing the graph, and the formula keeps changing. And another one. I mean, you can also assume linear and have like this is IV graph. So basically, the formula is graph dependent. So you can never skip the fact that you need to know the graph before applying identifiability results. Okay? But that's not feasible to keep listing all the graphical properties, right? Getting a formula for different graphs because they're infinite graphs. So what happened then is Jing Tian, this a very smart guy. He did his PhD thesis. He developed like an engine that for any causal graph you put here, you get a formula. And today there are so many though. So he developed this in 2002, but today there are so many extensions on let's incorporating experimental data together. Let's incorporate some parametric assumptions. But in the end, it's very similar. And this is called ID algorithm. So that is an algorithm that you don't need to now apply this graphical criteria to know what's the formula. You don't need the separation. You don't need anything. You just run the algorithm, but you need a graph. And once you have those two, you end up with a solution that's yes or no. And if it's yes, it's going to give you the formula. In this case, it's the front door formula, but it was given. Okay? So again, it's pretty general. But then you said, okay, I don't want the graph. It's too hard. So can we identify causal effects from the equivalence class that we just learned? And the task has been handled by many cases. So for example, the adjustment criterion is an extension of the backdoor adjustment. And the generalized adjustment criterion was developed by Perkovic. She developed this in 2018, where you can now apply the backdoor and the adjustment criteria directly in a partial ancestral graph. So this has been developed in 2018. However, we also recently proposed like extension of everything, calculus, algorithms for effect identification directly from PEG. So this was a paper from 2022. But with this, we actually can get rid of the graph completely. And which, for example, we can learn, since this is a representation of the equivalence class, we can learn the PEG using the FCI algorithm. And then we can have the answer, the same expression that we had before, fully from the partial ancestor graph. So this one was a backdoor adjustment thing. So you could have been able to apply just the adjustment criteria from Perkovic. But if you had like a more complicated graph like this, then the formula is different. It's no longer the adjustment criteria. We would not be able to solve it with the algorithm that she developed. But with the algorithms that we developed, is complete. So it doesn't matter the PEG you put here, we will get the answer if it exists. And in this case, for example, is also pretty complicated. And this is an open problem, though, to estimate these very weird equations. Because for propensity score, you need to assume, so if you have backdoor adjustment, you have propensity score, you have many ways of estimating it. But sometimes if you have just that, you just sit and cry. But anyways, you know just that you need to understand how to compute the effect. There is actually a way to do that, but it's a nightmare. And this basically complete the pipeline, right? So you can fully learn any PEG and don't care if it's going to be a backdoor adjustment and fully get the expression. All right, yeah, this is here. So I want to bring you, how much time? Yeah. So I want to bring you one application that I apply everything that you saw today, and you can do the same now because you learn how to do. So we had this data set that came from the psychology department in Münster, the University of Münster. They wanted to know if that is a causal relationship, and they don't know the direction between your microbiome, your gut microbiome, and mental health, which was depression in the case. So they had a lot of patients, and they had this idea that maybe that is an influence. They don't know if it's your mental health affecting your gut microbiome or the other way around, or maybe nothing, it's just diet. But actually, we could learn a graph. So as I said, we can account for latent confounding using the FCI. So I don't need to use the 2,000 bacteria that they provide me. What I did first, so with the help of some students, Leon, he's a PhD student there. He did the differential abundance analysis where he first identified bacteria that were associated with major depressive disorder. And to be causal, you need at least to be associated, right? So this is the minimum requirement. And we don't care if we didn't get all because it's accounting for latent confounding. And we selected 4 variables that were highly correlated. And we started getting some robustness tests because I said here, this was, you need to make sure that the condition dependence tests are correct. But this was a graph that in the end, we put together the bacteria and we found that 2 of them, Egertella and Hungatella, they actually have a causal effect to major depressive disorder. And the BMI is here, so it's not actually the cause of the association. So the association is regardless. So after conditioning on your obesity, and diet is probably around here, even accounting for that, that is still a causal effect. right? And actually that was seen when we computed the causal effect. And we did even like stratified by obesity because the clinicians were worried about that. But you can see that this is for Hungatella, is this variable here. The more Hungatella you have in your gut, the higher is the interventional probability. So this is really the probability of having depression given due bacteria. So it's the due there. So if you change only the abundance of bacteria in your gut, you increase the probability of having depression. And the green one is for non-obese patients. Then you have the yellow, that's obesity 1, and then the red one. So of course, the more obese you are, the weaker is the effect, but it's still, all of them are significant. So you can see that the 95% of the confidence interval here doesn't include the 0, so it's significant. So it actually increased. These are like some bars where we just did a threshold. So if you move from 10 to 31, for example, you have a big increase in the probability of having depression. And we did the same for Egertella. They have similar patterns here. So it's pretty nice. Like we did everything in a fully data-driven way, right? And of course, this has to be validated in a lab because you see it's still data-driven. But that's possible. This is very good for guiding experiments now. You cannot instead of going to the lab with 200 or 2,000 bacteria, they can start with this 2 and and then this is actually something that you can inform for this decision making. So I can actually develop a treatment that intervene on these variables if they are actually confirmed in the lab, and this is going to clearly change help you to prevent. Of course, these are not the only causes, right? So when I say cause here, that is a path, and they could have many other causes to depression. I'm not saying that these are the only cause, but this contributes to. This is the meaning of causality. And I continue working on the application side. So just a few things just for curiosity. I've been working on different projects. For example, that is this malaria research with the University of São Paulo, where they went to a very small city in the Amazon forest. And there in Brazil, the malaria is different than malaria in Africa, where people there get malaria all the time, and it's very mild, so they don't die with that. But there are some interesting things that some people never get immune, and they just keep getting it, and others get immune pretty fast, and they don't know why. So here is a very complicated structure. So we have no results yet. That's why I've been developing condition dependence tests for different scenarios. They have a very complex relational structure because first since they collected data for most of the households, first the people live together. So you have a confounding effect for the household. They also have genetic information. So you know how it's no longer IID, right? So all the tests that I showed here, they assume that you have IID data. So I need to first model the non-IID or relational structure of the individuals to then apply. But it's also a longitudinal study. And I now also need to account this. So it is basically going back to statistics and developing good statistical tests for that. But I think it's important for you to know that when you apply causality, you cannot just press a button and expect the results. There's a very hard statistical problem behind it to actually understand the causality. So this is one of them. I've been also working with single-cell multiomics data, which also has the relationship, like the cells are your sample, but the cells also are related to each other. So it's also a non-IID scenario. I just get anyways, if you're interested, I just opened a PhD position to work with brain networks. It's a very complicated task though, but the idea is that we have neurons, and neurons are also not your unit, your sample unit. So first you need to learn what's your unit, because neurons, they activate each other, and then they are coupled. So if you think that neurons are your samples, they are also non-IID. So you need to first know what is a unit, and then model the causal graph for the entire brain, but this is a lot of variables, so you need to do some sort of causal abstraction. So have like a higher view of the causal model after, so this involves causal representation learning, causal abstraction, dynamics, because this is also time series data. So it's a very interesting project. And also I have many works now with the medical faculty where we work on epidemiology studies. In the methodological side, you probably already had an idea of how many challenges we have. So especially in the single cell data analysis that I told you, people actually have mice and they can do experiments. And that's pretty fun because we can not only validate the results, of course, in mice, and then you probably have a transportability task later on, but you can also do causal discovery incorporating experimental data. And but the algorithms today, they don't account as with the uncertainty that I told you, so that we've been working on this. Also, this is the part of the malaria study where we are developing condition dependence tests. I also want to go beyond linear models. So we are developing like the condition dependence tests with non-linear functions, also accounting for temporal, spatial, genetic, and everything there. And cyclic models, I just started also going in the direction of using the FCI. Then you have sigma separations, longer separate. There are so many things that you change once you have cycles. So, but I want to go beyond that because, as I told you, so many dynamic systems. So if you go to infectious diseases or brain analysis, you need to single cell data. The cycles are always there. So if I don't go in this direction, I will have issues. And the scalability. So as I said, I did a graph with 5 variables. And there are strategies, so there are ways of doing abstraction and work on very big clusters, and then you have like a way to put together in a small graph over clusters. But it's still like you need to now know how you start small and increasing the size of the graph in a reasonable way. And since we have this score, I've been working on this direction. So I didn't cover everything. So causality is huge. There's like people working in different directions. So just for you to know, causal representation learning, causal abstraction is very popular today. Representation learning means I first need to learn what a variable is. So this is very important for images. So pixels are not your variables. You need to learn what a variable is first. But once you learn a variable, you also can go up. Like maybe you don't want the graph over the minimal representation of your figures, or even like in the brain situation, even if I learn what a sample, what a unit is, like what a group of neurons are, I want to go up. I want to abstract the model and see this in a high level way. So this is what causal abstraction is. Also causal reinforcement learning. So yesterday you saw the lecture by Zita where you see that reinforcement learning is actually inferring causality, but there are some people also incorporating as a model in your reinforcement learning algorithm, the graph. And there are very interesting questions of how you do exploration and exploitation, leveraging not only observational data, but also the graph if you have the graph. Not many works though on learning the graph in this process. This would be very interesting. Data-driven covariate selection, as I said, you don't need to learn the PEG to know the variables. If you are going directly to adjustment, there are some ways of doing this in a data-driven way, not for adjustment only, but also transportability. Transportability means getting and affecting a population and transferring to another population, because if the populations are different, you cannot just transport. That is a way to do that. Partial effect identification, in the case that you have a no answer, you can still get some bounds. Causal design of experiments, which is in the direction that I told you. Anyways, there are so many topics: individual treatment effect, which is more counterfactual reasoning, fairness, mediation analysis, and many more. Anyways, I'm really happy. Anything that's involving causality, I'm happy. So if you like it, I'm happy to discuss or collaborate. And yes, that's it.
Hello, thank you for your lecture. So the lecture mostly is about applications in medical settings. But at the start, you mentioned that causality could be or is is the missing piece to reasoning in language models.
It's a, yeah,
Yeah.
I think so, but it's hard.
Yeah. My question is, could you give an example how this would be used? Because I can see that reinforcement learning is, in some sense, very related to causality, the things you talked about here, but it's confusing to me. What would be our endogenous variables there? How would we model that?
Yeah. So reasoning is in different levels, right? So I try to bring the ladder of intelligence together with the ladder of causation. I think today LLMs are trying to reach the true SEM because it's a generative model. You want to use one model in the functional level to observe values. This is too hard. I don't even know if this is possible. But reasoning can come in different levels. So for example, if you simulate things and you see the output as a probability distribution, like you work in the expectation of things, you don't even need to go to the SEM. You can stay in the second layer of causality and maybe use this to infer the interventional probability distribution. Another thing that you saw here is that the layers, they never collapse, almost never collapse. And that's why I always have a question as my input. I never say, what's my full model? What's my full graph? I always ask, what's the effect of X on Y? Is that one edge? So if you have one question, it's already very hard. You want a very broad and general generative model that answers everything for you. So which means it's like getting all effects identifiable for the second layer of reasoning and getting identifiability of the, I think it's too much. I think that's definitely like I don't know, people are working for maybe no end. But I think your reasoning is important. So you can get like a simulator for one particular edge and see what's going to happen there. And then for me, like foundation models, large language is like one probability distribution because you're fitting. And it's really hard because it's also, you have no idea what a variable is there, which abstraction is there. So that's why I don't work with it. Maybe in the future when I see, okay, I know what I'm doing here, maybe I use it. But today it's already hard to work with tabular data over 5 variables. So that's why medicine is where it's just easy. Not even easy, it's easier. But I have no question. Yeah, no answer.
Okay.
By the way, but I think people are seeing a lot of results because there are some results for identifiability of the SEM, right? So for example, if you have causal sufficiency, and if you know that your functions are all monotonic, which for example is the case of the additive noise models, and your functions are nonlinear, your error term is Gaussian, so this is monotonic, you have sufficiency. Then you get the neurocausal models being a good approximator of your SEM. Maybe that's why we are seeing some results, but I think it's too much. We don't need it. We can do much better if you think, let's just answer one particular question. We don't even need the SEM. We can sometimes just do effect identification, counterfactor identification. Sometimes this is done from data, but it's small.
Okay, thank you.
One more question only. Just because let me, before the question, just have something. So as you know, there's a panel discussion this afternoon at 2. Adèle will be in the panel. So there's more chance for more questions about this stuff. Adèle will also be here after the panel, before the afternoon talk. So there's a lot of time for questions about causality. And so the panel this afternoon at 2, it's open to all the university. So there'll be more people probably, but you have priority. So try to get here like 10 minutes before the panel time so that you guarantee to have places. Probably it will not be full, but just in case.
And wear your
Um,
badges.
Sorry?
Wear the badges.
And wear the badges. Right. So having said that, we have time for one more question. And because, you know, time is schedule is tight today.
So last question here.
Thank you for the talk. So are there ways to combine the causality toolbox with some mainstream machine learning, such as language models for like tasks such as automated decision making for like, say, supporting clinicians' decisions or something?
Your question is if you can use machine learning to do.
Like, can you use the toolbox of causality to combine it with some kind of system, like with more mainstream systems like that are based on like language models, for example, to basically improve the capabilities of these let's say agentic systems, like using the causality to make the decision making more rigorous or something?
I mean, you can always use, for example, for example, large language models, you can think as a common sense, and then this is bringing knowledge. Maybe you can incorporate this in causal discovery, but I always see the other way around, how to put machine learning in the causal framework, not causal framework in machine learning, because machine learning is one probability distribution that we're trying to get there. So either you are reaching the full identifiability of the SEM, and this is maybe what people are trying to, and this is too hard. I think the other way around is more feasible. Like you can do all the estimation part via deep learning and incorporating large language models as one estimator of something. But today, I don't see the link.
Thank you.
Thank you.
Thanks. Yeah.